So we are saying the difference between a cetose and an aldose is the function. Now, they both come from one family, and that family is called the carbonyl function. Now, the carbonyl function is divided into two. We have what you call the aldehyde function, and the other one is what you call the ketone. In English, in French, it's called the cetone function group. So glucose, galactose, D-mannose, L-mannose come from the family of aldehydes, and they form sugars called aldose. Then fructose, unfortunately, comes from the group or the family called cetose, and it forms cetone and forms a glucose molecule, no, not a glucose molecule, a sugar called cetose. Cetose, get me correct. Then the difference that lies between these two families, the aldehyde family and the cetone family, is the double liaison that is with the carbon atom and the oxygen where they lie. The aldehyde is at the first carbon atom. The cetose or the cetone function is at the second carbon. So with this information, just this information that fructose is an aldehyde, and the rest, glucose, mannose, D-mannose, L-mannose, and all those things are aldose or aldehyde functions, then you are okay with the chapitre Glucides. Then you guys did stereochemistry on these glucose, maybe say sugars. So we said, just a summary of what you guys did last time. So we say that fructose and glucose are what you call isomers de fonction. Then we have glucose and galactose as epimers. Then we also have galactose and D-mannose to be diastereoisomers. Then the last one is D-mannose and L-mannose, which are enantiomers. So for now, we are not going to go into detail about which one is an epimer and what an epimer is, what is a diastereoisomer, enantiomer, all those things. No. For now, we are going to study the cyclic structures of these glucose, these sugar molecules, not glucose, right? These sugar molecules. So for the stereochemie of these functions, we are going to look at them in organic chemistry. So are there any questions so far? Okay, so today's chapter is on the structure cyclic de sucre. So before we even start looking at these structures and all these things, there are two types of representations. It's what we call the Tollens representation and the Haworth, something like that, representation. So the Tollens representation is something like Fisher's projection. You guys have done Fisher's projection tapes. Fisher's projection. Have you done Fisher's projection? Oui or no?
We didn't do it in detail.
But you did. You did. The question is, did you do? The question is, did you do?
We've used it before, yes.
Okay.
Yeah, we did, but
no. The question is, the question is, did you do? No, I just want to say, find out, did you do it? You say yes, we did. Then we come in now. We explain how it comes about. So there's what you call the Fisher's projection. We're also going to do Fisher's projection in organic chemistry, so don't worry. So even not explaining into detail what Fisher's projection is here is not a problem. C'est pas la peine. We are going to explain. There is actually a topic for Fisher projection, Newman projection, and what is the other one? There's also conformers and all those things. But for now, I just want to show you how these structures come about and their liaison. That's the main idea here. So we have what you call a representation de Tollens et Haworth. So we know that glucose is an aldose. Okay, so we know that glucose is an aldose. Now, it being an aldose, it's supposed to form a liaison with its other function in the glucose molecule in its own, like the whole glucose molecule. You see the glucose molecule being, you know that the glucose, in other words, a glucose molecule can either be considered to be an aldehyde or an acetal. So it's called, glucose is actually called, or bien the aldehydes that are formed in sugar are not fully, considered to be aldehydes. When they carry out like oxidation, partial oxidation, they oxidize to acetals. Now, acetals are alcohols with two alcohol functions. Now, the alcohol function is the OH. So you see that glucose molecules in their own way, they are what you call partial aldehydes. They're not fully they're not full aldehydes, but they are partial. Now, why are they partial? It's because with their oxidation, they are oxidized to acetals. Now, acetals are like, before going to an alcohol, you're supposed to pass through the acetal function, now go to the alcohol. So the acetal function is basically an alcohol with two function groups. It can also be called a diol, but in this case, we call it an acetal because it has got two function groups of the alcohol. You know the alcohol function. Alcohol function is OH hydroxyl. So in this case, we are saying that now this is the buildup, because what I'm going to start from is what I'm going to do kutidi. So please follow through. If you have a question, please stop me, because we'll be adding information. At the end of the day, we apply everything now in the travaux dirigés. So we are saying that glucose molecule being an aldehyde. Now, in this case, in the representation, the tollen, which is this representation here, that looks like a Fisher's projection. You see, it looks like a Fisher's projection. Now, when there is no hydrogen atom here, so the hydrogen atom here can be lost in a form of dehydrogenation. Yeah, dehydrolysis, where you remove water from a compound. Hydration is the addition of water to the compound. Dehydration, or bien dehydrolysis, is the removal of water from a compound. Now, we know that the water molecule is made up of two principal ions. We have the hydroxide anion and the hydrogen ion, which is also known as the hydronium ion. Now, in this case, there is going to be one loss of the hydrogen ion here, so that we have a liaison. The reason why you have this liaison structure here, so that you have a liaison with the carbon number 4 and the carbon number 1. The liaison is between carbon number 1 and carbon number 4. So this liaison is now what you call furène. So liaison on carbon numéro 1 et carbon numéro 4 forms a liaison called furène, a furène liaison. Now, this liaison is basically for all ceton function groups. It is for all ceton function groups. Then, now, when there is a liaison between the first carbon atom and the fourth carbon atom, it's going to form this type of representation. What shape is this? This is a pentagon. 1, 2, 3, 4, 5. It's going to form la representation de Haworth, which is in a form of a pentagon. Then, in addition, you have what you call alpha. You have what we call alpha glucose. I think you guys have seen this. And you have what you call beta glucose. So the difference between the alpha and the beta glucose is basically the orientation of the hydroxyl groups. So if the hydroxyl group is facing kumamba, and these hydroxyl groups are also facing on top, it's called an alpha glucose. It's called an alpha glucose. But if there is one that's facing kumulu and the hydroxyls are facing down, it's called a beta glucose molecule. So you have, like, sometimes you might have molecules like alpha D glucose, alpha bien beta D glucofuranose, all those things. So now some of you might ask me a question. Now this is just a representation to just show you, because the glucose molecule in the Glucides, we're going to be studying every chapter that is going to do with glucose molecules, Glucides, Chanshan. We are going to use the glucose molecule because it's our reference. Just like we did with our fructose, galactose, and other things. Glucose, we know that glucose, like I said, glucose is an aldose. It's an aldose. Now, some of you ask me a question, say, Daliso, you're saying the furan bond is supposed to be formed with the cetose. Now, why do we have the glucose molecule here? So the glucose molecule here is basically just a reference or bien an example, because the glucose molecule is the basis of the glucides. So all glucides come from the glucose molecule. So when we do stereochemie, when you understand what the stereoisomer is, when you understand what an epimer is, when you understand what an isomer de function is, when you understand what an enantiomer is, you'll be able to maneuver these functions here. Because the only difference between fructose, mannose, D-mannose, L-mannose, and the galactose is just the functions. The other one is found this side, the H is found this side, this OH is found this side, the other one is found this side. That's the only difference. But the structure of the glucose molecule will forever be the basis of the glucides. So I repeat. So what I'm trying to say is all cetone functions, or bien all cetose, cetose molecules will always form a liaison with the carbon number 4 and the carbon number 1. And their liaison will be called a furan. Their liaison will be called a furan. Their liaison will be called a furan. Now, in this case, if we were to apply this now on the cell, when I mean cell, and the only cetose we know, which is fructose, it means the liaison will be on carbon number 1 and carbon number 4, and the liaison that is going to be formed is going to be a furan. And if the molecule we are studying is fructose, it's going to be, for example, if it's a D-fructose, it's going to be D-fructofuranose. It's going to be D-fructofuranose. The furanose shows that there is a liaison between the carbon number 1 and the carbon number 4. Are there any questions?
Just kindly repeat your explanation.
Okay, so we are saying there's what you call representation de Tholen and representation de Haworth. So the glucose molecule here stands in as a reference point. So I said the furan liaison, or bien this is what you call oxidic bond. It's an oxide bridge. You see there's oxygen here. It's an oxide bridge. There's what you call the oxide bridge and glycosidic linkage. So between two glucose molecules, or bien two sugars, you're going to have what you call glycosidic linkages. Now, between the glucose molecule on its own and the what you call it, the functions on its own, when it's on its own like this, when it's on its own, it forms what you call oxide bonds or oxide bridges. Now, in this case, we are saying the glucose molecule stands in as a reference. So it stands in as a reference, but furan liaisons, or bien furan oxidic bonds, will always be formed from a cetone. Furan oxidic bonds will always be formed from cetones. Then we are saying this bond lies between carbon number 1, which is here, and carbon number 4. It lies or is defined only for cetose, cetose sugars. It is defined for cetose sugars. Cetose sugars. And the only cetose we have is fructose. So we are saying if this was a fructose molecule, now it's just a glucose. If it was a fructose molecule, we would have said it's going to be D-fructose, which is fructose, fructose. Now, because when you're naming it and you're supposed to make the liaison and all those things, it's going to become D-fructofuranose. D-fructofuranose. Now, the example we have here is glucose, and it's going to be glucofuranose. So take note, the cetose form a furan liaison with their carbon 1 and carbon number 4. and it is only for cetose, only for cetose. So the glucose molecule, I repeat, the glucose molecule you're seeing here is just a reference. Please, it's just a reference, because I said it is the glucose molecule that defines what an epimer is. It defines what a diastereoisomer is. It defines what isomer de fonction is. It also defines the enantiomer. You see, so the glucose molecule is the basis of everything. So like I said, know the structure of the glucose molecule. And when we study stereochemie, when you look at enantiomers, there are stereoisomers, epimers, functions, all those things, you'll be able to now know that, say, okay, this one is a diastereoisomer of this one. So the function here changes to this part. So this one is an epimer of this. This does this. Then this one is an enantiomer of this. This does this. So I'm pretty sure you guys have done stereochemie in your biochemie, but the stereochemie we are going to do in organic chemistry will be more comprehensive, and it will help understand which one is with the other. But take note, the glucose molecule will forever be the reference point for all glucides. The glucose molecule will always be the reference point for all glucide molecules. So in this case, this structure here that looks like the representation de Fischer is called representation de Tollen. Then this one here looks like the benzene molecule. It is called representation de Haworth. Are there any questions before we go any further?
Yes. Does it mean that the representation de Fischer is just the same as representation de Tollen?
No. Representation de Fischer and representation de Tollen are two different representations. With representation de Fischer, we represent the carbons asymmetric. Now, for now, bosses, that's why I said, for now, we shouldn't go much in detail. Just know that, okay, the structure, this one, is almost like the representation de Fischer, but I'll just give a bit of explanation. With representation de Tollen, we do not represent the carbons that are asymmetric. A carbon that is asymmetric is one that can either be chiral or achiral, which I didn't want to come this side. So, but for now, boss, representation de Tollen and Fischer, they are not the same thing, but they almost look like the same thing. Representation de Tollen has one thing missing. It does not show which carbons are asymmetric. If a carbon is asymmetric, we put to stars, to my étoiles. If a carbon atom is asymmetric, we put to stars. So in your stereochemie, we are going to say, okay, for a compound to be called chiral, it is supposed to satisfy two conditions. The first condition it's supposed to satisfy is that it's supposed to be it's not supposed to be superposable with its image. Number two, it's supposed to have no symmetry with any element. So if these two conditions are satisfied, it means that compound is chiral. And if it has a carbon that is asymmetric, then it also adds on to its chirality. So for now, the only difference that we are going to say, like for the Tollen and the Fischer, will be the Tollen has no form and does not represent which carbon is asymmetric, while the Tollen is just, the Tollen does not represent any carbon that is asymmetric. If a carbon atom is asymmetric, you are going to have to my étoiles here. Étoile is a star, so you have to my stars here showing that this carbon is asymmetric. Why? Because it satisfies the principle of chirality. Now, we're not going to go in much details about chirality. Then the Fischer shows which carbons are asymmetric. It's just like this same thing, but now Fischer shows which ones are asymmetric. Are there any more questions? Put your head. So, like we said, there's a question. Like we said on the other episode. No question. There's a question?
No, it's clear.
Okay, okay. So for representation, the Tollen, don't worry. I'll take note of the question. When we look at stereochemie and chirality, I'll bring it back and explain why Tollen and Fischer differ. It's because of the carbon asymmetric, which defines chilarity of different compounds. So in this case, glucose molecules or bien glucides, they also have asymmetric carbon. They also have their asymmetric carbons. But this is a representation we're using called the tollen, and we are not supposed to show which carbon is asymmetric. But with the Fischer projection or the Fischer representation, we are supposed to show which carbon atom is asymmetric, not symmetric, but asymmetric. Then therefore, we'll be like, okay, this one is chiral and this one is achiral. So when we start looking at the properties, physiochemie, and all those things, we are going to look at the what you call optique rotatoire. Optique rotatoire. But for now, we are on representation de tollen et Haworth. So this is another thing. Please take note. Aldose in your glucides, in the Q for glucides, you are always going to look at aldehydes and cetones. So when you are studying, make sure you know that, okay, this one is an aldehyde. So the differences that I ask you guys to research on, please put them on your heart, in your heart, wherever, but it should be from team. The difference between fructose and these other ones is very important, because when you come to nomenclature, it will be easy for you to say, okay, no, because of this condition, because in biochemistry, you only have conditions. For this condition to happen, there is supposed to be a factor. You see, so please take note that, okay, glucose is an aldose, then fructose is a cetose. Then from there, it becomes easy for you to decipher when you've been given a question. I'll show you how it's done when you're given questions on which one is supposed to come first in a glucose molecule, which one is supposed to come the second, and all those things. So now, representation, we get back to the core. So representation de tollen et Haworth. The same thing. Now, the liaison has changed, right? This one was liaison 1 et 4. 1 et 4. Now, this one is liaison 1 et 5. 1 et 5. The same glucose molecule here stands in as reference. This glucose molecule stands in as a reference. So the liaison between the first carbon atom and the fifth carbon atom form what you call a purene. A purene is an oxide bond. An oxide bond. Now, when you have glucose forming a liaison with fructose, when glucose and fructose form a liaison, their liaison is not called an oxide bond. No, it's called a glycosidic bond. A glycosidic bond, because you have two different sugars that are coming together. Take, for instance, a polysaccharide like cellulose or bien amidon. Cellulose is made up of small monomer glucose. Is it glucose or maybe say sugar molecules? So the linkages that make up the cellulose, are what we are calling the glycosidic linkages. Now, the linkage between the glucose molecule, just on its own, this one, where the glucose molecule envelopes itself and forms this type of shape, like a pentagon here, and forms like a hexagon, because this is like 6, 1, 2, 3, 4. Is it 5? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, 6. So it forms a. Is it a hexagon? It forms a hexagon. So the structure, because it forms like a hexagon thingy, its liaison is not called glycosidic. It's called an oxide linkage. It's called an oxide linkage. It's called an oxide linkage. So this representation here is what we're calling representation de Haworth, and this one here is what we're calling the representation de tollen. So the purene, which has liaison à carbone 1 et carbone 5, forms a liaison called purene, and it is for all aldose, aldo functions, ou bien aldoglucides. Aldoglucides. Are there any questions? Are there any questions? Okay. So now we're going to talk about, we're going to discuss on the principle, or bien the physiochemic properties of these molecules. So sugar molecules have got properties like solubility, how they taste in the mouth when you taste. Why? Okay, the question is why is that every time you taste sugar, it tastes. Why is that when you taste sugar, the cube one, the table sugar? What's the other name for table sugar? What's the other name for table sugar? Anyone? What's the other name for table sugar?
Sucrose.
Exactly, sucrose. So why is that when you taste sucrose, it tastes like it's sweet? Why is it sweet? Now we talk about esters and all those things. So the reason why sugar is sweet is because the alcohol function, the hydroxyl function, has got a tingling with the tongue. So what happens that in the human body, we have a lot of neuron transmission. You guys are doing medicine, so it's medicine. So in the human body, there's what you call like they are neuron transmitters. So you find that because you are testing a sugar molecule, you are just taking a sugar molecule, right? You are just taking a sugar molecule. But in the body, what's actually happening is the sugar molecule you are testing, because it has got a hydroxyl function, and the neuron transmitter that is responsible for any sugary taste has an affinity with the hydroxyl function. So when the two come in contact, the neuron transmitter that has an affinity for the hydroxyl function and the tongue that is supposed to have a sensation from that hydroxyl function, at the end of the day, because there is going to be that interaction between the neuron transmitter, because the neuron transmitter will be responsible for the reaction in the tongue. The neuron transmitter will be responsible for what's reacting in the tongue. At the end of the day, the hydroxyl that is going to be placed on the tongue affects the neuron transmitter. The neuron transmitter is a neuron transmitter. So it means it's going to send a signal to the brain. Then therefore, you are going to have a sweet taste. So the sweet taste does not just come because it's a sweet taste. No, it is because of the interaction between the brain and the sugar molecules on their own. The sugar molecules possessing the hydroxyl function, it plays that important role. In the same way, when you look at amino acids are the building blocks of proteins. So you have enzymes and all those things. So for things like enzymes, you have what you call an amino acid. It's a basic amino acid called histidine. So histidine is found on the active side of an enzyme. So you know what the active side does, Steph? The active side is the one that is responsible for all biochemical reactions. So when the active site is not in proper shape, you know, an amino acid, the reason why we have how can I explain? The reason why we have conditions like sickle cell anemia is basically because there is a deformity in the function, amino function, that is responsible for the normal bioconcave shape of the red blood cell. So if there is a dysfunction, or bien if the molecule, the histidine molecule, for example, has its carbon, which is asymmetric on position number 3. If that's the correct orientation of the carbon atom at position number 3. Now, if that person has it on position number 5, when that person has on position number 5, the same histidine molecule, the person now has a deformity, and they're going to have what you call sickle cell anemia. In the same way, like our professor gave us an example of mad people that are mad. Like the reason why they are mad in the biochemistry language is because the amino acids that code for normality, the ones that code for normality, like if the amino acid chain was supposed to be A, like 4 A's and 1 B. Now the person has got 3 A's and 2 B's. Because the mad person has got 2 B's instead of having 4 A's, because of that disorder, the person now becomes abnormal. That's why amino acids are very much important, or bien proteins are very much important for our diet. Because if there is any misfunction, if there is any miscoded amino acid, then the person becomes abnormal. That is why you have conditions like trisomy 21, where you have the person with squinty eyes. You guys have done biology. Steph? Hello?
Yes, we
Yeah,
have.
we can continue. Yes, yes.
No, I'm asking Kairi, kapena simache biology Kairi. You guys have done biology. There's what you call trisomy 21, which is also known as Down syndrome. So it's because of such factors. It's because of such factors that cause such conditions like trisomy 21, the eyes, shanshan, there's a mutation in the genes, and something there's Alzheimer's disease and all those things. But not forgetting the topic we are at. The topic we are at here is the physiological factors or beyond the physiological properties of these glucose molecules. So the first one is solubility. Solubility is basically the ability for a substance to dissolve in a solvent, not water, but a solvent. Water can be one of those solvents. So the first one is saying the O's or bien ozides are very soluble in water and very soluble in polar solvents. Examples here we have methanol and ethanol. Now the question is, those that have done advanced organic chemistry, those have gone a bit ahead. What's the difference between this one and this one? What's the difference between methanol and ethanol? Or bien, let me say methanol and methanol. What's the difference? What's the difference? Sure. So the difference is one is an aldehyde, the other one is an alcohol. So then we also have polyosides. Then polyosides, we have the polyosides are like polysaccharides. So we have cellulose and amidon. These are very insoluble in water. So it's a very short query. Then we have pouvoir rotatoire ou bien pouvoir optique rotatoire. So the reason why you have what you call is it the reason why you have sugars like this, right? The reason why you have sugars like D glucose. You have L glucose. D glucose, L glucose is because of what you are calling pouvoir optique rotatoire. Because of what you have, it's called optique rotatoire. So glucides have the ability to diverge light. You know, these compounds, when there is a projection of light, they have the ability to diverge light in a positive direction, which we are calling the dextrogyl, and in the negative direction called the levrogyl. So in organic chemistry, we are going to cover how we name compounds based on pouvoir rotatoire. Then pouvoir sucrant, which we are just from explaining. Sucrose or table sugar is formed from two simple sugars, glucose and fructose. So the liaison between glucose and fructose is called a glycosidic liaison. But the fructose molecule, if it wants to form a structure like this one, a structure that is a representation on her worth. If it wants to form a structure like that one, it's going to form what we are calling as oxidic linkages. So everything, the simplest thing you're supposed to retain or remember is this oxygen. The oxygen will show you that, okay, this is an oxidic liaison. Then we say all sugars are sweet because they contain hydroxyl, which are particular orientations that can interact with the taste receptors for sweet in our tongues. Then we are going to talk about action des acides 4 with a sucre. So when an acid 4 is reacted with a sucre, it forms what you call a fural. So a fural is an aldehyde that is furan with the hydrogen at position 2 substituted by a formyl group. So I won't go much in detail. So whenever you have an acid 4 and it's reacting with a sucre, it forms what you are calling a fural. A fural. Then number 5, we have réaction d'oxydation par métal de transition. So we have oxidation by transition metals. So what is oxidation? So oxidation can be defined in how many ways? It can be defined in 4 ways. What you call electron transfer, the gain of oxygen, the loss of hydrogen, and the last one, which is the oxidation state. So you find that in every oxidation reaction, there is need for reduction. That's how it is, right? A redox reaction, is accompanied by oxidation and reduction. So now in this case, oxidation. Now what happens? So we have a metal. You have a metal here. You have a metal. This is a glucose molecule. You have a metal. Now the metal has changed its oxidation state from +2 to, what's the oxidation state for copper here? What's the oxidation state for copper here? Those that have done chemie, those that have done chemistry, what's the oxidation state for copper there? What's the oxidation state for copper in copper 2 oxide? What's the oxidation state for copper in the molecule or in the compound copper 2 oxide? You guys, simple chemistry. When you're doing the chemical formulas, what were you guys doing? You write C with a plus and 2 kashan, then you cross multiply. Now, when you cross multiply, you find that the 2 comes this side. So it means that this one has a valency of 1. In other words, the oxidation state of an atom, an element, is equivalent to its number of electrons it's supposed to lose or gain. In some cases, it does not apply. The number of electrons that one needs to bond is not equals to the oxidation state. Why? It's because you have what you are calling a variation of oxidation. Some are stronger oxidants, some are weaker oxidants. So now when you react copper, there's a compound here for copper. When you react copper with any glucide, now this glucide is supposed to come from which function, from which family? It's supposed to come from the aldehyde family. It's supposed to come from the aldehyde family. If it comes from the cetose, it will not react. It's supposed to come from the aldehyde family. So when you react a glucide that comes from the aldose family with a copper compound, a copper complex compound, it's going to form what you are calling a brick rouge or bien brick red precipitate. A brick red precipitate. You guys know what a precipitate is, Steph? If you don't know, you say no, I don't know.
Yeah.
So what is a precipitate? The one that said we know. What's a precipitate? What's a precipitate? You said you know.
Let me just try. The solid stuff that remains after reaction.
Exactly. Exactly. So a precipitate.
Yeah.
Okay. Too much data. So exactly. So a precipitate is a solid that is obtained after a precipitation reaction. So this reaction you're seeing here, where you have a copper 2 complex. It's called complex because you have those things that you guys were doing in your chemistry. You know, you dissolve hydroxide, you dissolve excess ammonia, all those things. When you study what composition they have, you find that they form complex cations or bien complex anions. So the complex compound that you have here, when it reacts with the aldehyde, it forms a carboxylic acid. Now, when it forms a carboxylic acid, there is a precipitate that's going to be obtained at the end. Now, this precipitate has a color of, we call it brick rouge. Brick rouge is brick. You know what a brick is there? This is physical features, not biochemistry, physical features. You know what a brick is there? A brick, pan brick. Guys, pan brick, means a pan brick. Guys, look, you see, if you don't respond, it demotivates me. It's like, you know how Zoom is. I'm also having that disorder in the amino acids. So you respond. If I say, do you know this? You say fast, then we continue. So yeah, so this is where the name comes from. Brick rouge, a brick, there are those bricks that are reddish. So it looks like that. So when you have a precipitate that's a brick rouge, then you are saying that this one here actually contains an aldehyde function. It contains an aldehyde function. Now, you're saying that it contains an aldehyde function. And we said that aldehyde has its function defined on carbon number 1. The aldehyde has its function defined on carbon number 1. So theta D. If you are going to have the reaction, you are supposed to make sure that the carbonyl function est libre. The carbonyl function is supposed to be free for you to have this type of a reaction. So it also implies that even if the glucose or bien the glucide molecule we are going to study, even if the glucose molecule we're going to study has a carbonyl function that is not libre, if it's not libre, even if it's an aldehyde glucide, it will not react. So the condition here is for this reaction to take place, if the brick rouge is supposed to take place, we are supposed to have a carbonyl libre, which is free. It's supposed to be free for us to have this reaction. I'll repeat. So we are saying there is oxidation par méthode de transition. So we have a copper complex compound that is going to react with our glucide, not glucose, but any glucide molecule. So when it reacts, it's supposed to form a precipitate that's a brick rouge. Now, the precipitate brick rouge is a positive indication that this molecule we started with is an aldehyde. Or bien, it's an aldose. It's an aldose. Now, there's another condition. If the brick rouge is not formed, if there is no brick rouge precipitate, there are two conditions. One, it's either the carbonyl function group, which is defined at carbon number 1, is not libre. It maybe is in a liaison. Rule number 2 might be maybe the molecule we were using here is not an aldehyde, maybe it's a ketose. So there are two conditions. The first one is the carbonyl function is supposed to be libre. That is defined at carbon number 1. Note, we have two carbonyls. Right? We have what you call the aldehyde and the ketone, or bien the ketone. Now, in this case, we are saying the aldehyde, not ketone. The aldehyde is supposed to be defined at carbon number 1. If it is defined at carbon number 1 and it is an aldose, it means you're going to have a brick rouge precipitate. And in another case where you have an aldehyde, it's defined at carbon number 1, but the carbonyl function is not libre. If the carbonyl function is engagé in a liaison, like either oxidic liaison or bien glycosidic liaison, it means you are not going to have any reaction. So all in all, this reaction here is what you call liquid de Felling, yeah, something like that. Yeah, something like that. So is it clear? Is it clear? Because we're going to use this for the TD. Is it clear? Here, is it clear? Or to make it twice?
Daliso, for when you say the carbonyl is libre, what do you mean? Like it's no longer attached to the
no. When it's libre,
it's 4 o'clock.
When it's libre, it means it can allow another thing to be bonded to it. It can allow something to come and bond to it. So if it's libre, it means it's not engagé in any liaison. But if it's not libre, it's either, there are two conditions again, it's either it's engagé in a furane liaison or bien a purane liaison, or the other part which may be a glycosidic liaison. Now, a glycosidic liaison is that made between two glucides. Example is glucose and fructose. So the liaison between fructose and glucose, the liaison between them is called a glycosidic liaison. Let me just show you to just make things a bit clear. So we have so say sucre, sucrose, sucre, sucrose. So what am I trying to say? You should tell me if you can see what I'm sharing, right? Can you see? I'm on the internet now. I'm on Google.
Yes.
Yes.
So,
Okay.
I haven't got the correct image. So we are saying this liaison here is what you're calling the glycosidic liaison. The liaison between two glucides. It's called a glycosidic liaison. The liaison between this, because this is glucose, and we said glucose forms a liaison on carbon number 1 and carbon number shani.
Number.
Carbon number 1 and carbon number 5. It forms a liaison on carbon number 1 and carbon number 5. It's an aldehyde, so it forms the aldose, and aldose form what you call purine, and purine is defined at carbon number 1 and carbon number 5. So carbon number 1 and number 5 are formed this liaison here. They are formed this liaison here. Then we have fructose. Now fructose also forms a liaison here with carbon number 1 and carbon number shani.
4.
Exactly, carbon number 4. So carbon number 1 and carbon number 4 is for fructose, and fructose is a cetone. It's under the cetose function of glucides, and forms a liaison called the furane. It forms a furane. So when it comes to nomenclature, we are going to name these glucose molecules in regards to their liaisons that they form. So for example, just give an example, what we're going to name this molecule is called sucrose, but when we use the nomenclature usual is sucrose, but maybe in nomenclature international, we are going to say glucofuranosyl. Then we're going to put where the liaison is for the glycosidic linkage. Maybe if it's 1 or 4, we're going to say glucofuranosyl A5 fructofuranose. So we're going to say glucofuranosyl A4 or bien A5. It depends with the number of the liaison oxidic. Then we're going to say fructofuranose. But for now, this is just the explanation in Taonga. So this is the glycosidic linkage. Then this is the oxidic linkages. Like I said, please, the oxygen should be your guide. When there is an oxygen in the molecule in itself, that is called an oxidic linkage. Then this one here, between the two molecules, it's called a glycosidic linkage. Any questions? So we forge ahead. Then any questions? Vipanga sense? What's happening? Is it making sense?
A bit.
A bit. What's happening? It's not making sense. Guys, I'm told that it's Vipanga sense, guys. It's a watch it. That's Vipanga sense. That's Vipanga sense. Is it making sense?
Can you kindly repeat on the
You guys, should we end the class or what? Should we end the class? And where should I repeat? Why should I repeat? Samuel, why should I repeat? You guys, tell me why I should repeat. No, I'll repeat, no problem. No worries, I'll repeat. It's like biochimie if you got different na organic chemist, na chemie general lie. You guys, please, why should I repeat? You want that time up?
On the question Taonga just asked.
I told you that today is cool for biochimie. Packet series. So if you delay me, Nishi, Tataya. No, I'll explain. Don't worry. We can even schedule it for another day. The idea is, like I say, is to understand. So Apache re-explain. I'm not sure my doctors and my engineers. Yapaka data right? Yapaka data. You have to be strong for you to be a doctor. Eh? You have to sort out these structures. You have to put them in the head. You have to know. Okay, this one is this one is this. So what's the question, Mr. Samuel? What's the question? You can see the sharing now. Okay, let me use this one. Okay, it even explains everything for me. Can you see? Eh?
Yes.
Guys, I said you tell me if you can see. So we are saying you can see. So Tawanga's question, Mr. Samuel, was what was the question, Tawanga? I've even forgotten.
I wanted to find out the carbonyl libre we were talking about.
Yeah. So if a carbonyl function is libre, it means it is not engagé in any liaison. So if you look at this one here is the carbonyl. Is it the carbonyl? No, this is not the carbonyl function. The carbonyl function is this one here, because the carbonyl function is where you are going to have all these liaisons together. Now this one is not libre. Yeah, this one here. It's not libre because there is this liaison. So when it comes to giving its nomenclature and studying this molecule, we're going to say, no, the carbonyl function for this one is not libre. It is engagé in a glycosidic liaison. It is engagé in a glycosidic liaison. It is engagé in a glycosidic. So when there's this interaction, because one of you, the thing is, sometimes you guys don't ask these questions. Okay, you know that glucose is a carbonyl, and this is also called a carbonyl, and their functions, they also have oxygen and oxygen. Now, one of you is supposed to ask, okay, Dali, so if it's a carbonyl and both have got oxygens, what about the other oxygen? Where does it go? So in a reaction where you have the two glucose molecules interacting, there's always going to be a water reaction that's going to be taking place. This one here. You see, every time you have a reaction between these two, there is always going to be a water reaction that's going to take place. So now the problem is you guys not asking, is it clear? So if it's not engagé in a liaison, it means it's libre. But if it is engagé in a liaison, it is not libre. Is it clear? Is it clear?
Before we move, I saw something on your Google page. May you go back? Those where you're showing us molecules that were like not yet bonded, so just individuals.
Oh yeah.
Yeah. Maybe you can start explaining from there. I don't know.
Start explaining from there.
Yes, like how they bond and what happens to each carbonyl group.
No. As in this part, for where the bonds come in, Shan, that's the TD now. That's the travaux de regime. I'm supposed to explain how the liaison come about, which one is double, Shan, all those things. So all that part is saved for the TD. All that part is saved for the TD, because in the TD, we're actually going to name these molecules using these reactions that you're seeing here. All these reactions that you're seeing are going to be the basis of our nomenclature. So we're going to look at how this one interacts with this one, then the liaison forms with this one, then this carbonyl function is libre, this one is not libre, so there's not going to be a liaison, there's going to be a liaison, and hence the suite. So can I continue? I have taken note of your question, Taonga. We are going to look at the reactions in detail. Do not worry. We are going to look at the reactions in detail. Any questions? Before we go to the last, is it the last reaction? Any questions? Samuel?
Yes, you can continue, boss, but
if it's sharing. Sorry. Now kamba guys that waliko sharing mwe opazona. Anyway.
Brain yazima, boss.
Guys, we should close the class. We will continue another day. What's the suggestion?
Let's continue following at least.
We're asking, even the girls should say, should you continue or should stop?
Yes, let's continue, Daliso.
Is it interesting? Is it interesting or it's boring? To see.
We are getting there.
Alhamdulillah. No, don't worry. If you want a revision, we can still. I'm chapter 1. See pressure. With me, there's no problem. We can still start from chapter 1. So the other one is the other reaction is oxidation of halogens. So the oxidation is douce mélange. Then it is done in the presence. You know what halogens are? Halogens are group 17, via group 7 elements found on the periodic table. You have astatine, you have iodine, bromine, fluorine, and chlorine. So their reaction, please take note of these two small. They look small, but when I start doing my reaction, kuja taonga. When I start doing reactions, nomenclature, how reactions come about. I know, so please, this reaction you're seeing, it's not like my decoration. You should also take note. So when iodine or bien a halogen reacts with a glucose molecule, there's oxidation, and again, the fraction of the aldehyde at carbon number 1. For this reaction to take place, the carbonyl function is supposed to be libre. It's supposed to be libre for us to form, if it's a glucose molecule, a gluconic acid. If it's a mannose molecule, a mannonic acid. If it's a galactose molecule, a galactonic, etc. If it's a fructose, it's supposed to be fructonic, all those things. So when you have oxidation of halogens, the positive reaction, so the reaction starts here. The first reaction, when you have a glucose molecule reacting with what's this? A glucose molecule, a glucide reacting with the copper ions, it's supposed to form a brick rouge precipitate. And we said there are two conditions. The first condition is it's supposed to be an aldehyde. Okay, it's supposed to be an aldehyde. Now, if it's an aldehyde, it will definitely react with this complex compound. Now, if it is not an aldehyde, it means the reaction will not be positive. It will be negative. It will be negative. Then the second condition was, even if this is an aldehyde, for as long as the carbonyl function is not libre, it is engagé, if it is in a liaison with any other molecule. It's not only another glucose molecule that can be engagé, or bien fructose, or bien galactose. It can also be engagé in a liaison. We're going to look at osazones and all those things. It can be engagé in a liaison with a phenyl function. So the idea is the carbonyl function is supposed to be libre, it's supposed to be free. There is no need for the carbonyl to have another molecule or another compound or another atom bonded to it. Those are the two conditions. So the first condition for a positive reaction is we are supposed to have an aldehyde, and the aldehyde automatically, an aldehyde is an aldose. Then for the second condition, the carbonyl function is supposed to be libre. So there are two. The first one is supposed to be an aldehyde, and the second one is the carbonyl function is supposed to be libre. Any questions? Then it's the same principle now with halogens. So halogens in alkali milieu, the same with carbonyl function libre. We are supposed, if the carbonyl function is libre, we are going to have these products, the gluconic, mannonic, galactonic, etc. But if it is not libre, it is not going to react. Now, I was expecting one of you to ask me this question, and unfortunately, no one has asked me this question so far. So why is it that on all the reactions, even though we're not completed, just these first two reactions, we're only talking about aldehydes and all those things? What's the answer? Someone to tell me the answer, because you guys have not asked that question. I'm asking you that question. Why is it we're only talking about aldehydes and not the other part, the cetones? Why? Why are we not talking about cetones? We're just talking about aldehydes. You know, aldehydes have done this, aldehydes have done this, the function is supposed to be free, the function is supposed to do this, etc. Anyone with a response?
because most of the sugars are outdoses. That's what I think. Yeah.
No, okay. Anyone else? Very good try. Very good try. Another one. Why is it okay? Hey, as in the thing is, you guys you're not taking note of these things. It's like the question is, why is it that we're only talking about aldehydes, this, aldehydes that, aldehydes this, aldehydes that, aldehyde this, aldehyde that? So the answer is these reactions that we are doing here, the reactions that we're going to do for this school are basically just going to justify the aldehyde functions. They're just going to be defining aldehyde functions. They'll be disqualifying cetone functions. But there are also cetone tests. These are just like tests. So if you want to test for, just like we're doing for photosynthesis, is it, what color was it? Red, black, blue, black, something like that. All those things. They just justify that, okay, this is this. So whatever is, like this is like opposite, boy, girl. Whatever is contrary this, whatever is opposite with this is for the cetose. So these tests we're going to look at are basically just going to justify the aldehyde functions. They're going to disqualify all cetones or cetose. They're going to just disqualify all those things. But they are actually tests for cetone functions. Is it clear? Is it clear? Because most of the things we're going to talk about no, this reacts, it will be just aldehydes. It just will be aldehydes. Travel the okay, we're almost there. So, any questions? So
before we move on, Dalisa, on the halogens, may you repeat what you said?
I said a halogen will always react with an aldehyde. Now the aldehyde is supposed to satisfy two conditions. Now the aldehyde here, when I say, guys, another thing, when I say aldehyde, you should know that I'm talking about the aldose. So the aldehyde is supposed to satisfy two conditions. The first one, the aldehyde function, that is carbon number 1, is supposed to be libre. Condition number 2 is it's supposed to be an aldehyde, actually. It's supposed to be an aldehyde. The first one is it's supposed to be an aldehyde. The second one is it's supposed to have a libre liaison for the aldehyde function. The first one is it's supposed to be an aldehyde. The second one is it's supposed to satisfy the liberty on the first carbon atom, that is where the carbonyl function for aldehyde is defined. So I'll repeat. First condition, it's supposed to be an aldehyde. Number 1, it's supposed to be an aldehyde. If you can see, all these things are aldehydes here. The aldehyde glucose, aldehyde sugars. Glucose is an aldehyde, that's what you told me. Mannose is an aldehyde, you also told me that. Galactose is an aldehyde, and they are called aldose. So it's supposed to be an aldose or be an aldehyde. Then for you to have these acids like gluconic, mannonic, galactonic, it is supposed to be, or bien it is supposed to have a carbonyl function that is libre. If it has no carbonyl function that is libre, therefore there will be no reaction. There will be no reaction. There will be no reaction. Is it clear?
Yes, it is. Thank you.
Alhamdulillah. Any questions? Any questions from anything we've done so far? Just ask me. I'll still go back and explain. I know there are a lot of things that you guys are supposed to assimilate, but is there any question from anything we've done from this side? All the way from Sucre, Cyclique, you can ask any question before we forge ahead. I even think TD will be postponed for another seance to just allow you guys to read through this, because if I start explaining about the liaison and how they form here, we know as a bracket. So is it clear so far? You can ask me any question from all these things we've done. We'll still do that. Yeah.
May I please see the first, second, and third property?
Oh, you're writing down. No, I'll send you this PDF. There's no need for writing. Oh, you have a question here. The first, second, and third. Now I'll send it. I think I sent this PDF in your group yesterday. Dave? Yeah. As in, were you copying, or maybe you have a question here?
Can you please explain the second one again? I
The
didn't
pouvoir
understand.
optique rotatoire. Eh? The pouvoir optique rotatoire.
Yes.
Okay. So please, guys, just tell me no. So go back. That's my job. I'm supposed to explain where you do not understand. But at the end of the day, we didn't know what pouvoir optique rotatoire is, what solubility is. You tell me no. So before you go any further, please, bosses, vacation even 3 times, 4 times, I'll still explain. I don't want to rush, because if we rush, we'll crash. So what we said about pouvoir optique rotatoire, we said the glucose molecules, or bien the glucides. Mr. Samuel asked me a question. Say, okay, Mr. Deliso. Now this is how I'm going to answer it. So you should follow me. Samuel asked me a question. Say, okay, Mr. Deliso, what's the difference between the representation de Fischer and the representation de Tholen? So I was like, okay, the representation de Fischer is different to the representation de Tholen because of one key factor, and that key was the asymmetric carbon atom that we have. Now, because we are saying these glucides have asymmetric carbons, we are going to define asymmetric carbons. We know in organic chemistry. So I said, for you to define an asymmetric carbon, there are conditions as well you're supposed to follow. You see, if a carbon atom is asymmetric, you are going to follow certain conditions. Then later on, you say this molecule is having maybe 3 asymmetric carbon atoms. Maybe it's having 2, maybe it's having 5, all those things. Now, it is because of the asymmetric factor that now we talk about the pouvoir optique rotatoire, the power of optic rotation, or bien optic activity. So we have what we call dextrogyl compounds and levrogyl compounds. So when a molecule is subjected to lumiere, and this lumiere, sorry, but for you that wants to go deep in this, you can also look for spectroscopy. It's a topic in chemistry. It's called spectroscopy, how compounds interact with light. Yeah, but what we just explained now is you find that this glucose molecule, when it's subjected to a special type of light, it's a special type of light, not just light, any light, no, from the sun, no. A special type of light. A special type of light will now cause the molecule to deflect, or bien, it's like a stimuli. Its response is positive. So if it has a positive response to the light, the light that you are subjecting this molecule to, if it has a positive response, we are calling that response a dextrogyl, and the molecule will be called maybe say, okay, let me say, so it will be called D-glucose, because when this glucose molecule was subjected to a special type of light, it had a positive reaction to that light. It had a positive reaction to that light. So in this case, when I say positive, right, positive can also mean negative. Like if it's going towards the light, it can mean it's positive, or it can mean it's negative. It depends on which factor. Now, in this case, we are talking about it having an affinity, or maybe it it's reacting towards the light. It's going towards like what you guys call phototropism. Is it phototropism? Where you have a plant and it's reacting to light in a positive way. Then we have, what is the other one? The negative one. I think there's a negative thingy for that one. It's reacting away from the light. So in the same way, when the molecule here has a positive reaction with the light, with the light, I said this light is very special, not lumiere de la soleil, no. There's special light we use in chemistry. That's why I said for further details, if you want to go really inside what happens, you should look up spectroscopy. Yeah, so this is what happens. The glucose molecule interacts with the light, and the reaction is dextrogyl. The reaction is said to be dextrogyl because it is it's in a positive orientation. It's positive D. It's positive. Then if it's otherwise, if it's the opposite, if this glucose molecule was subjected to light, if it was subjected to light, then it reacts negatively to the special light that this molecule is subjected to. If it reacts negatively, it will form what we are calling the levrogyl, which is the negative orientation. So to sum up now, what I'm trying to say is, if the glucose or bien any glucid molecule is subjected to optic, there's a special light there. There's a special light that we subject molecules to for us to check if it has got asymmetric carbons. If it's chiral, it's another case. But if it's got carbons that are asymmetric, then we test them. Say, okay, no, this is a dextrogyl, this is levrogyl. So because of the principle of asymmetric carbons, we also have these dextrogyl and levrogyl. So when the glucid molecule is subjected to this special light, it will react in a positive way, and that positive way will be called D. That's the reason why you have got D glucose. Like I asked the question, so what's the difference between L-mannose and D-mannose? So Samuel said the difference between L-mannose and D-mannose is because they are enantiomers. We are not going to look at that now, but yeah. So because of that orientation, the other one is D and the other one is L. The other one is D and the other one is L because of their affinity towards light. Then there are also contributing factors. It can also be now, like the reason why maybe it's in a D type of orientation is because the hydroxyl function, for example, would say maybe this hydroxyl function changed. It went to the other side. This hydroxyl function went to the other side, and this hydrogen is on the other side. So because of that, you find that it's going to be called a D-glucose molecule. Then if it goes back to this normal orientation, it might also affect the name, and it will be now called L-glucose. So there are factors that affect the dextrogyl and levrogyl orientation, but they come from the light. It is because of the light that we have the dextrogyl and the levrogyl. So the dextrogyl is the positive interaction of the molecule with the light, and the levrogyl is the negative interaction of the glucid molecule with the light. Any question? Is it clear, Esther?
Yes, it's clear.
Any
Thank you.
question? You're welcome. Any question? Any question? Any question on anything? On anything? Even things ahead, we can still answer. So we're talking about oxidation par les halogènes. Les halogènes. Was it this part clear, or I should repeat?
Can repeat both.
Okay. So we are saying oxidation par les halogènes. So it's an oxidation that is very, very soft. This is a calm oxidation. So we are saying in the presence of iodine and bromine in an alkaline solution. What's an alkaline solution? An alkaline solution is one that contains a concentration of hydroxide ions higher than that of the hydrogen ions. So that is what we define an alkaline solution to be. Now we're saying for us to have positive reactions, you are supposed to satisfy two conditions. The first condition is supposed to be that the molecule we are looking at is supposed to be an aldehyde. It's supposed to be an aldehyde. Then the second condition is, if it is an aldehyde, of course, it is supposed to have a carbonyl, which is the aldehyde function, of course, is supposed to be libre. Now, what do we mean by libre? It's supposed to be free. It's supposed to, we're not supposed to find it in any liaison. It's not supposed to be found in any type of liaison. Either be it glucosidic, it be oxidic liaison. So there are two types. I say there is glucosidic and oxidic. So oxidic, we have furanose, and furanose also known as furan, and we also have purane, also known as puranose. Any questions? So we have the glucose that forms galactonic, the mannose forms manoic, and the galactose forms galactonic. Any questions? Any question? Any question? Huh? So we go to the are we finishing the code today? So we have what you call formation des ozones. So ozones are just like isomers. Now glucose molecules, when they reacted with phenyl hydrazine. So let me just maybe let me make it this way. All these reactions we are looking at are just tests, right? They're just like tests for us to find out, like, no, is this a glucose molecule? Is this an aldehyde? Is this a cetone? Is this all those things? These are just reactions. Just define those tests. Yeah, when you're defining those tests, we're also going to define the properties. That's what is happening here. So we'll be defining bit by bit. Say, okay, it's an ozone, then what happens if it's an ozone? So we are saying, from your definition, you told me that glucose, mannose, fructose, and all those things, they are all the same thing. They're all the glucose molecule, just like the fructose, just like the mannose. But the only difference comes in when you have the isomer de fonction, when you have the difference, like when you look at here, the hydroxide functions are on the same side. This one here is different. This one here is also different. You have the carbonyl there, all those things. They're all this, the glucose molecule is the basis, like I said, is the basis for all these things. It's a basis for all those things. The only difference is maybe where the hydroxide function is found for one molecule, where the carbonyl function is found for the other molecule, where the primary alcohol is found for the other molecule. So when you react glucides like glucose, fructose, and mannose, just these three, right? When you react them, glucose, fructose, and mannose, when you react them with phenylhydrazine, when you react these glucose, fructose, and mannose with phenylhydrazine, they form what we are calling ozone. They form what we are calling ozone. Now, ozones are of the same structure. So if you look at this structure, and look at this structure, and look at this structure, they are all the same. This is an ozone of glucose. It's called D. So ester, the D here stands for the dextrogyl. So it's D-glucose, phenylhydrazine, or it can be called glucoozone. It can be called D-glucose phenylhydrazone, ou bien glucosazone. Glucosazone, yeah. Then we have the second one here, which is fructose. So when fructose is reacted with phenylhydrazine, it's a D, so it's a D. So we're going to have D-fructose phenylhydrazone, which can also be called fructoosazone. Then the last one is mannose, D-mannose. We are going to have D-mannose phenylhydrazone, which can also be called mannozazone. So I said an ozazone is formed from the reaction of from the reaction of either a glucose plus phenylhydrazine, a fructose plus phenylhydrazine, a mannose plus phenylhydrazine. They form ozazones. Take note, galactose does not form an ozazone. Galactose does not form an ozazone. Galactose does not form an ozazone. So mannose, fructose, and glucose, when they are reacted with phenylhydrazine, they form ozazones. So the first one here we have is D-glucose phenylhydrazone, aka glucoosazone. The second one will be called, it's a D. If it was an L, we would have said L. It's going to be D-fructose phenylhydrazone. Then the last one here will be D-mannose phenylhydrazone, which is also known as mannozazone. Any questions? So we go to the, see, this is the last time? No, okay, we have another one. We have the second last reaction. So the second last reaction is réaction de perméthylisation. Réaction de perméthylisation. Now, perméthylisation is an analysis that is used to define the positions of the glycosidic linkages between reducing sugars, or bien reducing sugar residues. Sugar residues. So perméthylisation is a classic way or approach to establishing the position of the glycosidic. The glycosidic is in capital letters, the glycosidic linkages between sugar residues. So what actually happens in the reaction of perméthylisation is that sorry. Hey, this is dangerous. No, sorry. So it gives the position of the what do you call them? Glycosidic linkages. Then it's also going to help us. It is also going to help us understand what type of bond lies between a glucose or a glucid molecule. In a glucid molecule, we said we are going to have the purine for the aldose and the furane for the cetose. The perméthylisation reaction is an approach to determine the position of the glycosidic linkages between glucose sugars. It can also help us to determine the position of the 1,5 purine and the 1,4 furane. So in other words, the reaction de perméthylisation is just a determination reaction for the two types of linkages. We have what you call the glycosidic liaison linkages, or bien the oxidic liaison, which are the furane and the purane. So basically, the perméthylisation reaction is the reaction of iodine, or bien methyl diode. In French, we say it's backwards. Iodine methyl with our sugar, of course. Then we are going to have an ether. An ether is going to be formed here. An ether is an oxide organic compound that has an alkyl at the far end and has the rest of the molecule on the other side. So what actually happens is the glucose or the glucide molecules react with methyl diode and they form an ether. So depending on the ether. So we said an ether is an oxide of an organic compound. This is an oxide, right? Now, on the right-hand side, either bit on the right or on the left, Sesalamem shows, we are going to have an alkyl group, not an alkane, but an alkyl group, either methyl, propyl, butyl, hexyl, ecosyl, all those things on the far end. But we are supposed to have an oxygen. We are supposed to have an oxygen. So the reaction de perméthylisation now states we are supposed to have hydroxyl functions that are libre for us to give ethers of methane. The hydroxyl function is supposed to be libre for us to give methyl esters in the presence of iodine. So from the reaction of methyl diode, we are going to obtain these methylic ethers. Methylic ethers. So I'll make a resume for this part. So we are saying reaction de perméthylisation is a reaction used for the analysis of glycosidic linkages, of course. It can also help us determine which type of liaison is found in a glucose or a glucid molecule. Now, the glycosidic linkage, like we defined, is a liaison found between or formed between two glucides. Two glucides. An example we gave is sucrose. Sucrose is formed from glucose and fructose. Sucrose is formed from glucose and fructose. The liaison between fructose and glucose is what we are calling the glycosidic liaison. Now, the representation de Haworth shows us the orientation of the carbon number 1 and carbon number 5 of the glucose molecule. So if there is an interaction between the carbon number 4 and carbon number 1 and carbon number 4, if there is an interaction, then we are going to have a purine formed there. We're going to have a purine formed there. Now for the fructose part, the fructose being acetose forms a liaison or interacts with the carbon that is on position number 4 and the carbon that is on position number 1. And they form a liaison called furane or furanose. So the two liaisons that the independent molecules form on their own, there's what you call the purane for the aldose molecules, and you have what you call the cetose, what is that? The furane for the cetose. The furane for the cetose. So the perméthylisation reaction actually helps us to determine the bonds that we are going to have. Is it going to be an oxidic bond, or bien it's going to be a glycosidic linkage? Linkage is the same as a bond. And we said for this reaction to be defined, we are supposed to have a hydroxyl function that is supposed to be free in this glucose or bien glucid molecule. So the reaction takes place in the presence of methyl diode, which is also known as iodine of methyl. So at the end of the reaction, you are going to have the production of ethers. An ether, like I said, is an organic oxide that contains on the other side a function, either be it theo, a ketone, an aldehyde, a nitrate, amide, etc. But for as long as you have an oxygen bonded to another alkyl group, it is called an ether. It is called an ether. So an ether is a compound, is an organic oxide that is formed from different, where you see in organic chemistry, in biochemistry, in all these organic modules, when you see R, R represents the rest of the molecule. The rest of the molecule can either be an alkene, it can be alkene, alcane, ethyl, an alcohol. It can be anything. This R represents anything. But the main key here, we are talking about methylic ethers. We are supposed to have an oxygen bonded to a methyl. Then we are saying an ether is an organic compound with the rest of its molecule being an alcohol, an ether, etc. We're supposed to have the liaison of oxygen with an alkyl, For as long as you have a chain this side and bonded to oxygen with an alkyl in the middle, it is called what is this? An ether. Guys, I'm exhausted, Moisa. Last part A. TD on severa, inshallah. So the last part is l'action d'acide periodique. So what this basically does is cut the glucid molecule into parts. It just cuts the glucose molecule into parts. So when the acid periodic reacts with a molecule like this one, it first cuts it in one portion that is acid formic. The other one is acid aldehyde formic. So the function, the alcohol primaire, the primary function alcohol gives the aldehyde formic. So this part here, this part gives the aldehyde formic as a result of the acid periodic. So acid periodic on just cuts this molecule in two parts. The first part is for the alcohol primaire, which is this one here, and the other part is for the alcohol secondaire, which is this one here. Then we are going to have the formation of aldehyde formic from the alcohol primaire and function acid formic from the function d'alcool secondaire. That is all you're supposed to know on l'action d'acide périodique. Guys, Ninaka, any questions? Hey. Any questions? Any questions? Are there any questions? Please, if there are questions, even from the first, I'll take them. Where you do not understand, I'll re-explain. Where you did not understand, I'll re-explain. Are there any questions? Are there any questions? Because I'll start asking questions now. Are there any questions? Are there any questions?
Question. Based on the same properties you've been giving us, can you re-explain on the explanation of how the glucose precipitate is formed?
The glucose.
What reacts with? Yes.
Okay. Any other question? This part.
Yes, this same one.
Any other question? Mr. Samuel, I'll ask questions.
We talked about the galactose not undergoing, is it the phenylazone? I don't know. So what's the reason behind galactose not undergoing the same
Ozone reaction? Any other question? Guys, I need questions. Because TD will need a lot of understanding from these things. So if you don't ask me these questions now, then TD, it will be a bit hard for you to understand. So ask me questions. I'm still here. Ask me questions. I have two questions. The first one is the reaction here. We explain the mechanism of the reaction. And the second one is why galactose does not form an does not form ozazole. Why galactose does not form ozazole? So, Samuel, any questions? Samuel, any questions? Who else? Kondwani, is it Kondwani? Is it Kennedy? There is Fumbani. That's the question. Bless, any questions? Any questions? Then we have Kennedy. Any questions, Mr. Kennedy?
Okay, I'm just confused on the part you're saying if carbonyl libre. I'm failing to understand it.
You're failing to understand the carbonyl libre part.
Yeah.
So then the other one, let me take note of these questions. The other one, no other question.
Okay.
So the first
one question.
The first one, just a minute. The first one is the phenyl reaction. The second one is why galactose is not forming an ozazone. The second one is libre carbonyl. Keep them coming. Keep them coming. The other one is
yeah. So like on this same part, reaction, oxidation, blah blah blah. You mentioned that provided the conditions are met, it's an aldehyde, carbonyl libre, the reaction will be positive. Otherwise, it's going to be a negative reaction. I didn't understand the positive and negative.
The positive and negative reaction. Okay. So it still comes back to the first question. Any other question? Please keep them coming. So we go to Lillian. Is it Lillian? Any question?
No, I wanted to ask on the question Blessings asked.
Who is this next? Esther. Any questions?
No.
No questions. So I should ask a question.
Okay. Can you re-explain on the last property?
Acid periodic. So acid periodic. Then we go to Blessings. Blessings already asked a question. Teps. She's already asked a question.
Yes, I asked the first one.
Okay. Then Madame Taonga, any questions so far? Before I start asking questions.
No, I don't have any questions.
So I ask a question. I asked a question.
Okay, sure.
Okay, so now explain to us why is it that in the reaction number 5, this reaction you're seeing here, in the reaction number 5, why is it that for us to have a positive reaction, we are supposed to satisfy 2 conditions? Or in other words, just give an explanation of what you heard on reaction number 5. I'll still re-explain it. Just give a reaction on a brief sum. Mr. Kondwan, any questions? No questions. So, Taonga, you can just explain what you understood on reaction 5. The floor is yours, madam.
So, what I understood is that when glucose here is oxidized, there should be a free carbonyl. Yes, there should be a free carbonyl after the oxidation of glucose. And then they should also be a precipitate, a brick-red precipitate. Yes. And then yes, that's what I remember. And then we looked at something about something like a glyco something bond. That's yes, that's what I remember.
Like what?
A glyco I'm not sure. A glycosidic? Yes, a glycosidic bond. That bonds if we're maybe to mix fructose and glucose. Glucose. Yeah. A glycosidic bond forms them, and yes, that's all I remember.
Okay. So for those that ask this question, should I explain, re-explain? Or it's clear?
No, re-explain.
Okay. So we said the reaction Cenc. We said for reaction Cenc to take place, there is supposed to be satisfaction of two conditions. Two conditions. Condition number one. We are supposed to have an aldehyde. We are supposed to have an aldehyde. Condition number two. First of all, what's an aldehyde? Don't define an aldehyde to be a carbonyl, an organic compound that has the carbonyl function on the first carbon atom. Let's hope you took note of that definition. The definition of an aldehyde is it is an organic compound that has a carbonyl function. Now, the carbonyl function is defined on carbon number 1. I think I'm answering question number 4. I'm answering the one for reaction, the filling, and the one for, is it Libre? The one that asks, I don't get what Libre is. Then we go to the others on galactose. Then we conclude with acid periodic. Please, are there any other questions? So that we include them before we close. Because travaux de recherche, we won't do it today, we'll do it another day. I'll organize maybe next week, inshallah, or the other week, depending on how free I'll be. So, are there any questions? Before we conclude, we close once, Shanshan. Are there any other questions? Because these questions, I'm not going to check what there are a few. I know people have got questions, but they don't want to ask. So, are there any questions before we proceed? I
think
any questions?
For me, I didn't understand very well the three properties. Yeah, where we had the pouvoir
these ones. The first three. The first three.
These ones I didn't understand. Yes.
Okay. Please bring them. Bring your problems. We shall talk to the problems. We'll solve the problems. No, I don't want you guys to, every time you come for cool, it just becomes like I'm giving you more things to study. No, you are supposed to understand these things. Even as you leave the meeting, at least you've got one or two things. So if you have a question, don't be afraid to ask. Ask the question that you want to be answered. Ask me. No, that is we didn't understand here. Repeat. I'll repeat. Because my goal, I know I've made a presentation of 12 pages. It's a presentation of 12 pages. But I'm not supposed to finish the 12 pages. No, I'm supposed to make sure at the end of the 12 pages, everyone understands what the 12 pages had. Not just because, no, I'm supposed to know, finish, no. If you have questions, please. I know there's 2 questions there. There's 2 questions. Please, bring the questions now. Bring them now. So that we answer them. So, pouvoir rotatoire, solubility, and sucrant pouvoir. So, pouvoir rotatoire. Any other questions? I know there are questions there.
And also that part for the was a something phenylhydrazine.
Ndiye makwesheni tifuna kairi amene. Phenyl hydrazine. Any other question? I know there are questions there. Bring them. I can't just have 1, 2, 3, 4, 5, 6, 7. 7 questions, and you guys are 9. I need another one to add the question. So it means if I explain all these, because here there's a question on there's a question on reaction number 5, the explanation on question number 5, then there's an explanation on the ozone, then we have acid periodic, then we have the first part here. So if I explain on these slides, is it going to be okay for everyone? Because I think people do not have questions.
I suggest you just re-explain all the properties.
I re-explain all the properties.
Yeah, just to be on the safe side.
Okay. So this is what we're going to do. I'll re-explain all the properties. I don't know if you guys have got rendezvous, shan, but do you guys go for his idea? I explain everything from chapter 1 to chapter last, all the slides. Do smart. Are you okay? Or maybe you want a break, then we start.
We're okay with it.
Not bossing at me, okay, when I'm sorry, okay. No, tell me. You tell me. What's on your plan? I'm also a student like you. Tell me, should we go on a break, like 10 minutes break, then we come and continue, they say, explaining, or you just continue explaining? Do you guys have anything to do after 50? This is already 17 hours. So you tell me what we should do. If we break off for 10 minutes, then we continue, or we just continue explain. Tell me, I want you guys to be free with me whenever we're having class. So tell me what you want me to do. The girls, talk to me. The guys, talk to me. What are we supposed to do?
We can do it.
So, représentation de tollen est représentation de Haworth. So we say that the representation that is called tollen is almost identical to the representation of Fisher. But the difference comes in with Fisher's projection that defines the asymmetric carbon atoms. The asymmetric carbon atoms in a representation de Fisher is what differentiates it from representation de tollen. Representation de tollen can also be like a semi-developed, formula developed plane. Now, where you draw the skeleton of the carbon liaison from top to bottom, instead of them drawing like from left to right. Is it clear? So the difference between representation de tollen and representation de Fisher is the representation de Fisher has asymmetric carbon atoms, while representation de tollen is just a normal formula developed manje iambela from the top to the bottom. And we said for representation de Haworth. Now, representation de Haworth comes in as a result of the liaison that is formed with the carbon number 1 and carbon number 4. The liaison formed from carbon number 1 and carbon number 4 result in the formation of the Haworth projection, or bien Haworth representation. So we said that because you have a liaison at carbon number 1 and carbon number 2, we are going to call this liaison a furan in the case where we are talking or bien discussing about, well, not discuss about, discuss what. So we are talking about the cetose. If we are talking about the cetose, we are automatically going to have this type of liaison, which is the furan, And we said also that this type of liaison here is called an oxidic liaison, It's called an oxidic liaison. So are there any questions? Or let me repeat, then I'll allow a question. So I'm saying Representation de Tolen and representation de Haworth are representations that we use in day-to-day biochemistry to represent glucose or glucose glucid molecules. So here we said there was a question that was raised in the earlier Q. We said, Mr. DM, what's the difference between Tolen's representation and Fisher's representation? The response was, Tolen's representation basically just shows the skeleton of the carbon atoms, that is from top to bottom, with the adjacent hydroxide and hydrogen atoms. Whilst the representation de Fisher, we are going to look at this, like I said earlier on, in our organic chemistry, shows the carbon chain. Of course, it shows the carbon chain from top to bottom as well, but it also explains the principle, another notion of asymmetric carbon atoms. So I said in our organic lecture, we are going to explain how asymmetric carbon atoms come about and the principle or the notion of chelarity. So just to answer a question I had, that is it Blessing that asked about why galactose does not form ozazole, is because of the notion of chelarity. So the notion of chelarity, like I said, is supposed to be satisfied with two conditions. So the first condition is the image of that molecule, galactose, is supposed to be non-superposable and is supposed to it's not supposed to have any symmetry with any element. So now you find that galactose is a sugar. Of course, it also has carbon atoms that are asymmetric. Now you find that mannose, fructose, and glucose, they all have the same carbon positions that are asymmetric. Galactose also has carbons that are symmetric, but they are different. The ones for galactose and glucose, mannose, and fructose are the same, but it's only galactose that has one that is different from the other. It is for this reason why that the ozazole is not going to appear for galactose, but is going to appear for the three, the fructose, the glucose, and mannose. So away from that, I'll explain when we get there about Nancan, but I just want to highlight one point of chelarity and how it affects different substances. Maybe to just go away off topic, to just give a notion of chelarity. You see, there is those, you guys are doing medicine, eh? So last time we talked about aspirin. Any medicine, any either aspirin, etc., they are all made of organic compounds. So if aspirin is achiral, if it does not contain a carbon that is asymmetric, it means if a patient is subjected to aspirin, the person will not respond to it. Why? It is because the carbon that is responsible for the carbon atom that is responsible for its chelarity is not asymmetric. So you see that the principle of a carbon atom being asymmetric in compounds affects different things. Not only do we talk about these amino acids and changing form leads to different diseases, even just a carbon atom, if it's not asymmetric, it means something else. If it is asymmetric, it also means something else. So in this case, the representation de Fisher and that of Tolen are different because of just this small thing, the carbon which is asymmetric. And we said the liaison at carbon number 1 and that at carbon number 2 for a cetone or be a cetose group of sugars forms what we are calling a furan. So this is representation de Haworth, and this is representation de Tolen. There's also what you call Tolen reaction, but we're not going to go in detail. Yeah. So is that clear on the other side? Is it clear on the other side?
Dali, so before we move on, when we say carbon is asymmetric, is it that it has 4 different compounds around it? or that's
Exactly.
something else?
Exactly. It means that the substituents that are bonded to that carbon atom are different from each other. If they are the same, it means that carbon atom is not asymmetric. So please, also details. Or maybe I should explain what the carbon asymmetric is, just make things clear.
As in, like, okay, I'm trying to understand the difference between the Fisher representation and the Tollin, because if you look at this structure we have here,
This one, and that of the Fisher.
And that of the Fisher, just want to make a clarification. If you look at the last carbon, the 5th carbon, are we paying attention to the 5th carbon or the 4th carbon?
No, you're just looking about the representation. The representation.
Yes.
Without the furin, the thing, shan. Just the representation. We're not looking at any. Yeah, we're not looking at any carbon here. Like, no, specifically we're looking at the carbon. No. Maybe let me explain what asymmetric is. For a carbon to be asymmetric, it means the 4 substituents, or bien the 2 substituents, in this case, like for these ones that are in the middle, they are supposed to be different from each other. So when you look at this carbon atom here, how many substituents does it have? It has this one here, 1 hydrogen, 2 here, that's hydroxide. It also has the 3rd one, this whole thing, we'll call it a substituent, this whole thing. So it means this carbon atom is asymmetric. Same applies to these ones here on the middle. This one here has 1 hydrogen atom that's different from this whole thing. It has the 2nd one here, and the last one, this whole thing, it's also different. So when you go on, you find that some molecules only have certain parts of the compounds having asymmetric carbon atoms. Okay, take for instance the example. Here, instead of having the oxygen, we have our hydrogen atom. So this carbon here, if this was hydrogen, if this oxygen here was replaced with hydrogen, so we are saying a carbon that is asymmetric should have 4 different liaisons, or 4 different substituents that add 4 different substituents. So the first one will be this whole thing, the first substituent. The second one will be this hydrogen. The third one will be this other substituent. Now we have another hydrogen. Now the rule is we are supposed to have 4 different. The carbon atom forms 4 bonds, and we are supposed to have 4 different substituents. Now in the case where we're going to have hydrogen and hydrogen, that implies that this carbon atom here is not asymmetric. With representation de Fischer Taonga, we are always supposed to show which carbon is asymmetric. So, like I said, if this was hydrogen, with representation de Fischer, we are going to say, okay, CH with hydrogen, oxygen, we are going to put a star there, a star. We'll put a star on top there to show that this carbon is asymmetric. Same applies to this one, because there are 3 different substituents. Actually 4, there's this one here, 1, 2, 3, and this other 4, this whole thing. There are 4 different substituents. They are different. This whole thing is different from this thing, so different from this hydroxyl, so different from this rest, the rest of the molecule. So we are supposed to represent this carbon here with an étoile. The étoile shows that the carbon atom here at position number 2 is asymmetric. So it goes on. But here where we impose that this part contains or has a hydrogen atom, we will not include the star, because we know that this carbon here is not asymmetric. But this one here on position number 5, okay, say this substituent here is different, this one here is also different, this one is different, and this one is also different, then it's going to have a carbon which is asymmetric. So all in all, if we had the hydroxide here, it would mean all these carbon atoms are asymmetric. So with a representation de Fischer, we are going to represent them with an étoile to show that this molecule actually we are talking about is asymmetric. Then later on, if all the carbon atoms satisfy the principle of asymmetric Then we also talk about now the principle of chilarity, where a molecule is supposed to be superposable with its image, or non-superposable with its image, and should not contain any element of symmetry. So the difference basically between this representation and the representation de Fischer is only the representation of the carbons that are asymmetric. Any questions? Any questions? Okay, so we forge ahead. There's a question? So we forge ahead. So same principle applies. So representation de Tholen. Here we have a chain or a skeleton of carbon atoms. Now the liaison has now been moved. The oxidic liaison is now formed between carbon number 1 and carbon number 5. So the liaison here is now what we are calling the purine. The purine. And we are saying the purine is a liaison formed by the aldose. Formed by the aldose. So aldose are actually aldehydes, and the aldehydes form sugar molecules. So when the sugar molecules form from the aldehyde function, we call them aldose, and they are forming a liaison called oxidic. It's the liaison oxidic called purine. This liaison we call it an oxidic liaison, or bien oxidic pont. A pont is also known as a bridge in English. It's called the oxidic pont. Pont oxidic. So the pont oxidic here for an aldose is formed at carbon number 1 and carbon number 5, and it is called a purine. It is called a purine. So please take note. This is what you call a purine. It is formed by cetose, and it is at position number 1 and position number 4. Then representation de Fischer is almost the same as this one, but with a difference in the carbons that are asymmetric. The representation of the carbons that are asymmetric. Then representation de Haworth is basically the oxidic bonds that this molecule forms with itself. Any questions? Okay, so now we go to the properties of these sugars. So we said there are different properties that different sugars have. So we say these are physical properties and some are chemical properties. Talk about solubility. Solubility is a physical property. So we say solubility is the ability of a substance to dissolve in water. Aye. Now, it's not only water, but any other polar solvent. Because when you talk about the principle of solubility, you talk about the principle of polarity as well. Because they are what you call positive dipoles for polar molecules, and they are negative dipoles for negative polar molecules. So the simplest is this same one. All oxides and all oxides are very soluble in water and in polar solvents. They are soluble in water. What it means that they are soluble is, for example, when you put an equivalent amount of water to an equivalent amount of sugar, that is sucrose, in a cup, if they are equivalent, it means everything is going to dissolve. But in a situation where the amount of water is more than the amount of sugar, or bien the amount of sugar is more than the amount of water, you're going to have, like, there will be excess sugar, and you're going to reach what you call the saturation point, where there is no more sugar that can dissolve in the water. But the idea here is that all oxides and all oxides are very, very, very soluble in water. When you put them in water, they dissolve. Then polyoxides are not soluble in water. Now, a polyoxide is an example is cellulose. Cellulose cannot. It's a poly. Because of it being a poly. That's the reason why it's unable to dissolve in water, because there are a lot of glycosidic linkages that are supposed to be cut by the water molecules. Like before even starting the biochemistry course, there was supposed to be a course for water. Like you look at water and how its liaisons are oriented. so that you understand what happens when you are cutting a liaison, that is a water liaison, a hydrogen bond, when you are making one, etc. So that is it to do with solubility. Solubility is basically a physical property that states that a liquid or bien a solution is going to be able to allow another substance to dissolve in it. So there's what you call a solvent, a solute, and I've forgotten the other ones, but there's that chain. There's a solute, solvent, and I don't know what the other one is. So the idea is when the glucose or the glucides are put in water, depending on which ones they are, the oxides or bien O's, if they are put in water, they dissolve, even in polar solvent. Then if they are polyosides, if there are many repeating chains of these oxides or Oses, it means they are unable to dissolve because of their strong or because of their repetitive glycosidic linkages that occur, because this is a polyoside. So it means there are a lot of repeating units. Example, we have here cellulose. So it means cellulose is built from a small monomer, for example, it being glucose. Glucose à la puissance n. So we know that n can be anything, that is n étoile, anything starting from 1 to positive infinity. So now for us to break all those bonds, it will take a huge amount of water to break the liaison. So any questions on the solubility? Okay, alhamdulillah. Then we go to pouvoir rotatoire. So we said
yeah, sorry. With the question. Is insolubility also a chemical property?
Oh yeah, if solubility is a chemical property, when you talk about precipitates, it also is a physical property. When you talk about things like what we're actually talking about here is just like some physical properties. But when you talk about chemical properties, we explain that in the form of constants, like the solubility product constant, etc. But here we're just looking about like a physical property. We're just dissolving things. Okay, no, this can be dissolved in this. Yeah. Any questions? Any more questions? So we continue. So pouvoir optique rotatoire. So we said different glucides have different interactions with light. Now we said this is a special type of light. There are molecules that are going to interact in a positive way and those that are going to interact in a negative way. So we said, for example, we are going to say a seed has got two parts. There's what you call the plumule and the radicle. So the plumule is one that becomes the shoot, and the radicle is what becomes the root. Is it that the radicle is one that should stay, the one that goes in the soil? Then the plumule is one that becomes the shoot, isn't it?
Yeah.
Okay. Yeah. So in this case, when we are responding to light, I'm using this example just to explain what dextrogil and levrogil come in. When that seed is responding to light, the plumule always want to grow or bien respond positively to the light because it has a higher affinity for light. You talked about oxygen and all those things. Then there's another part, the radical, that always wants to go down in the soil. So it means it's responding to the light negatively, but responding to the gravity positively. So what I'm trying to say is you have compounds or glucides that are dextrogil in nature. They respond positively to a special type of light. Then we have those that react negatively to a certain type of light. This light, like I said, for those that want to actually understand what type of light and how the orientation comes in, you can look up what I stated to say spectroscopy. Spectroscopy. in spectroscopy, we understand how different molecules interact with different light wavelengths, because you know light is made up of different wavelengths. So with different wavelengths, it means a wavelength and frequency, they are inverse proportion. So it means with a different wavelength, there is a certain type of interaction. With another type of wavelength, there is another type of interaction. But the bottom line here is there are those that are going to interact positively with the light and those that are going to interact negatively with the light. Are there any questions here? Okay, so we also added on to say that Glucides have the power.
Like, are there examples of the same sugars that react positively and those that react negatively to the
It's actually
light?
So an example is glucose here. Glucose here has no, let me not use this one because is it okay? Yeah, this one, because this is glucose and it's an aldose forming a purine. Perfect example. So there is this glucose here. Now the glucose here has an orientation of D. That's dextrogyl. So this is an example of one. This is an example of one. Not forgetting that we have what in chemistry we have what you call enantiomers. We have what you call enantiomers. An enantiomer is when you put your hand on a mirror. When you put your hand on a mirror, what you see is an enantiomer of your hand. It is non-superposable when you put it. Shows it looks like your right hand. When you put your right hand on the mirror, it shows your left hand. When you take your right hand and your left hand, when you put them together, they are non-superposable. Even if you try to arrange them in any way, 3D, 4D, 5D, you won't find the perfect superposability. Now, it's the same thing here. When this molecule, when you get an enantiomer, in a case where you get an enantiomer of this molecule, an enantiomer, a mirror image of this one, it's automatic that you are going to have the L orientation. That is why I asked a question when we started the course. I said, what is the difference between L mannose and D mannose? The difference is they are enantiomers of each other and their orientation towards light is different. One is D dextrogyl, the other one is L levrogyl. The other one is dextrogyl, the other one is levrogyl. They are also enantiomers of each other. An enantiomer is a mirror image of another object. So when the glucose molecule is subjected to a mirror here, when you put a mirror, the molecule that you're going to find is an enantiomer of this molecule here, this glucose you're seeing. The thing that you're going to, or beyond the image you're going to have, is an enantiomer of this one here. So enantiomers of two molecules also result in the formation of counter optic rotatoire. So you have, if you have a D glucose molecule, its enantiomer will have L orientation. If you have L orientation, you have the D orientation on its image. But the bottom line is, like one of my professors had said, the D glucides are the naturally occurring glucides. The D are the naturally occurring glucides. Then the L are sometimes made in labs. They are all those things. They are those artificial glucid molecules that we can talk about. So the D are the ones that occur in nature, and the L are the ones that can be synthesized. So for amino acids, it also changes now. Amino acids being the building blocks of our bodies, they are what you call S amino acids, oriented in the S, and those that are oriented in the R. So now that one, now we explain the principle. We all go back to the principle of chelarity. We go back to the principle of chelarity and how chelarity interferes with these molecules. So The dextrogyl and the levrogyl are just orientations of these molecules towards light. The dextrogyl being the positive orientation, the levrogyl being the negative orientation of this light. So we said these compounds can also have enantiomers. An enantiomer is basically a mirror image of a particular object. So if the D-glucose is put on a mirror, whatever you're going to see on the mirror is an enantiomer. In chemistry, we don't say the image, right? We say it's an enantiomer of the object. Is it clear?
Yeah, it's clear.
Alhamdulillah. Any other questions? Apanis, do smart, just kalafa, do smart, just kalafa. Any other questions? Okay, so we also explained the principle of pouvoir sucre. We say that because in our bodies we have what you call neurotransmitters, and neurotransmitters are responsible for a lot of things. They are responsible for a lot of things. So I said it is because of the hydroxyl function that is also responsible for the taste, the sucre, the sweet that you guys taste. The sweet that you guys taste is as a result of the interaction between the hydroxyl function of these glucid molecules with the neurotransmitters of the brain. So it is because of the hydroxyl functions that we have the sweetness that we taste. Is it clear? This is just the simplest explanation I can give. Is it clear? The simplest explanation I can give. Like the hydroxyl function is basically the basis of how sweet these glucid molecules can be. Any questions? Pouvoir sucre. Any questions? Okay, forge ahead. Now we go to reaction 4. So reaction 4, we said when a sugar is reacted with an acid 4, when a sugar is reacted with an acid 4, it forms what you call a fural. It forms what you call a fural. So a fural is an aldehyde that is furan with the hydrogen at position 2 substituted by a formyl group. So like I said later in the course, I wouldn't want to explain the mechanism of this reaction because there are certain principles of what do you call them? A molecule that is apole, shinganan, all those things, like they are what you call Sn1 and Sn2 reactions. So for such kind of reactions, we are supposed to apply either Sn1 type of reaction or Sn2 type of reaction. So the bottom line is what you just have to know is when you react an acid 4 with a sugar, it's going to form a fural. A fural. That is what you're supposed to know. The mechanism, I'm told you guys for medicine don't do mechanism. So the mechanism is for me to know, not for you guys. So the mechanism is not important, but what you're supposed to take note is when you react a sucre with an acid 4, yeah, you get a fural. You get a fural. Any questions? Direct. There's a question.
What is an acid 4?
An acid 4 is a strong acid. An acid 4 is a strong acid. So a strong acid is one that does ionize completely. One that ionizes completely is an acid 4. The one that does not ionize completely is called an acid faible. Faible means weak. So an acid faible is one that does not ionize completely. Yeah. So a sugar plus an acid that is strong gives a fural. So give me examples of acids that are strong. People, acids that are strong.
Sulfuric acid. Hydrochloric acid.
What else? The ladies.
Nitric acid.
What else? Okay, forge ahead. So now, this is where the problem started
just
from.
Before we forge ahead.
Okay.
Wait, just before we forge ahead.
Yeah.
This futurals that we form. Is it something like maybe, let's say for example, we had maybe glucose acid 4, we're going to have maybe something like a glucofutural, or how does the name exactly come about?
I didn't go as far as getting the names of different sugars that are formed from futural. But in other words, I would say a futural is just like the way we say esters. We say an ester is formed when a carboxylic acid interacts with an alcohol. It's just like a general name. But I know there are glucose molecules that react with these acids and form their specific futurals. Futural is just like a general name. You get it? It's like a general name. I don't know what a futural of glucose is called. Maybe it's called glucofutural. I don't know. Yeah. But you can also do a research on that one. Then later on, you can tell me so that we share information about the same. Is it clear?
Yeah.
So yeah, futural is just like a name of a class, a class for compounds, that are formed when an acid 4, which is a strong acid, reacts with sugar. Then if you have a problem with a French word, please tell me. Then we explain, so that before you head together. Then we looked at the Cencum reaction, which is the oxidation of these glucides with metals, and these metals are transition. So transition metals, like we know, form variable valencies, etc. Now in this case, we have an oxidation reaction. So this is where the problem started from, like I said. So we said, for this reaction to take place, and like concluding to say it is positive, we are supposed to satisfy two conditions. The first condition is, this is just a preparation. I don't look at this reaction. This is just a preparation for this thing we're going to use for the precipitate. So the conditions that we have here, the first one, please, but this is where you're supposed to be writing down. The first one is you are supposed to react this molecule, this glucide here, with this complex compound. Now, this molecule here is supposed to be an aldehyde, or it's supposed to be an aldose. There's actually a reaction equivalent to this same one. I've just forgotten its name. Is it called dinitrophenyl? Should be one of the reactions. Yeah, I think it's dinitro. When I look for it, I forgot it. When I look for it, it should be dinitro something. It's the one that is used to define the cetose. It's the one used to define the cetose. So like I said, these reactions we're going to look at only justify the aldehydes or the aldose. There are also reactions that justify the, the cetose. So for this type of reaction, I'll look for the one that justifies for, the cetose. I'll send it in the group. Yeah. So we said there are supposed to be conditions for you to satisfy this positive reaction. So the first one is when you react this glucide molecule with this complex. It's a complex cation. It's just that we've put it in the form of like a redox reaction. So when you react this glucide here with this here complex compound, we are going to produce a precipitate that's a brique rouge, or bien it's going to be a red precipitate. Now, we are saying if it's going to be a red precipitate, it means it has justified or has been in alignment with two conditions. The first condition being this reactant we had was an aldehyde. This reactant we had is an aldehyde. And the second one being that the carbonyl function, which is the aldehyde function. Now here when I say carbonyl, I'm talking about this function here, this function here. Let me do this. Can you guys see? Can you guys see? Yankani, can you guys see?
Yes, we can. We can see.
We are talking about this function.
It's 6 o'clock.
It's 6 o'clock. Okay? 6 o'clock. We're talking about this function. Now, at position number 1, because when you're counting, when you go back to nomenclature, because this is a function, when you're counting, we'll start from here and say carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, etc. Now, we are saying this function is supposed to be libre. It's supposed to be just like this. It's not supposed to be engagé in any liaison. It's not supposed to be engagé in any liaison. So rule number 1 is you're supposed to be looking at an aldehyde. In this case, if it's a glucose sugar, it's supposed to be an aldohexose. Aldohexose is also another name that we can give for a 6-carbon glucose molecule. So it's supposed to be an aldose, just an aldose, okay? If it's an aldose, question number 2, is the function libre ou bien c'est engagé dans une liaison? If it is in a liaison, it means this condition cannot be satisfied. If it is in a liaison, it will not be satisfied. So take, for example, I'll use this principle of the enzyme and key lock theorem. So we know that an enzyme has what you call the lock, and the lock which is the lock which is called the active site, and the key which is called the one that goes inside the active site, the one that goes in the active site. So what happens to an enzyme if it is the active site is already occupied? What happens? Simple biology. What happens to an enzyme if it is already occupied by maybe say a substrate? What happens? What happens? This is just normal biology. What happens? Is the biology maibara?
It will not catalyze.
Exactly. There will be no reaction. There will be no reaction. Why? It's because the enzyme is already occupied. Same applies to this liaison here. We said if this liaison here, the aldehyde function is engagé, if it is already bonded to something. What I mean by engagé is it is engaged in another liaison. If it is bonded to something else, it's not going to react. If it is bonded to another function, it's not going to react. So the basic principle for this reaction is rule number 1. For this reaction to take place, for you to have the positive result here, for you to have a positive result, you are supposed to have an aldehyde, number 1. Number 2, this aldehyde function here, the aldehyde function at carbon number 1, the carbon that is number 1 here, it should not be found in any type of liaison. It should not be found in any type of covalent bonding. It shouldn't be even found in an ionic bonding if that's the case. It should be just free, just like this, the way you can see, just like this. So that you're going to have, now this is where the mechanism comes in, the mechanism of a reaction. So that when this interacts with this complex ion, it's now going to form a carboxylic acid. So you get now where the principle is. The principle is we want to maintain this function so that we have the formation of this carboxylic acid, because the carboxylic acid is just basically the addition of oxygen to the aldehyde function. We are going to have a carboxylic acid. So the principle, like I said, there's 2 rules. The first one is you are supposed to consider the molecule that you are reacting to be an aldehyde. Now, it being an aldehyde, and we're talking about the glucides here, it's going to be called an aldose. So this aldose is supposed to be an aldose. That's rule number 1. The rule number 2 is this aldose molecule is supposed to have a carbonyl function. When I say the carbonyl function, we are talking about the carbon atom here and this liaison, because this is what justifies this to be an aldehyde. The ketone has this double liaison on carbon number 2. The ketones or the cetones have this double liaison on carbon number 2. So I'll allow who's this? Taonga, please give us a definition of an aldehyde and a acetone, the one that you gave earlier on, so that we also just add on the same things that we have learned. So the difference between an aldehyde and acetone. You can go ahead. Taonga Doja.
No, I'm here.
Oh, okay.
Yes. So for acetone, we say that the carbon has a bond on the is it the first? No, has got a bond on the second carbon. Yes, and then for an aldehyde, the bond is on the second carbon. I'm confusing myself. Sorry, Delisa.
No, the aldehyde has the function on carbon number 1. Please, aldehyde, carbon number 1. This is carbon number 1. For acetone, it's on carbon number 2. Carbon number 2. Let me do this to just help with this quiz. Let's go on the internet so that you guys know what we're talking about. So say aldehyde and say ketone. So I'll be sharing my screen anytime soon, so that we just have an understanding where these things are coming from. Can you guys see? Yeah. So what we are saying is on carbon number 2, this R here, and this molecule, this R should be different from this other R. Let me look for another molecule. This one looks a bit uncanny. Okay, let me use this one. Maybe this one makes sense. I'm looking for those ones. This one, acetone. You can see,
Yes.
So acetone is different from an aldehyde, because I want you guys to look at this image first. Then when you are done, especially this one, when you're done, you should tell me. Then we go to this one. You see, we are saying the aldehyde is supposed to have its function on the first carbon atom. The first carbon atom is this one. There is no other carbon atom. The R represents whatever comes there. Maybe it can be the second carbon atom, or it can be another function. Is that okay?
Yes, it is okay.
Now with this one, we are saying the carbonyl function is placed at carbon number 2. So carbon number 2, in this case, when we count, this is going to be carbon number 1, and carbon number 2, carbon number 2, carbon number 2. Then,
So is that not carbon number 3?
Carbon number 3.
Yes, is it not carbon number?
How is it carbon number 3? 1, 2, 3. Okay. 1, 2, 3. Oh yeah. Sorry. It's on carbon number 3. Sorry. Guys, so it's on carbon number 3. So the idea is the positioning of the acetone is never, when you position, if you're drawing in your diagrams, when you're drawing acetone, and you position the function at position number 1, it no longer becomes acetone, it becomes an aldehyde. Maybe if I explain that like that, it becomes more clear. So we are saying R, which is in red, should be different from the R in black, which is this case. Where is this image? R, where is this image? Hey. R, where is it? I'll use the same one here. So you're saying R1 and R2 are supposed to be different. Then with the aldehyde, the first R, which is the R, the rest of the function of the chain, when you are counting, the function is supposed to be placed at carbon number 1. At carbon number 1. So for the cetone, it's supposed to be at position number 2. If you move it to position number 1, it no longer becomes a cetone, it becomes an aldehyde. It becomes an aldehyde. So an aldehyde always have CHO with like a hydrogen uku CHO. The hydrogen always by the end. Now for a cetone, like you guys clarified for me, you said the function was at position number 3. So the cetone can neither be at position number 3, number 4, number 5, etc. But should never be at position number 1. That is why we are saying it should be at position number 2 to be different from that of the aldehyde, because the aldehyde function is defined at carbon number 1. It is defined at carbon number 1. Any question? Any question? Okay, forge ahead. Please, if there are questions, ask them. Also, should make another call for Shani. So we go to, is it clear for those? There are those guys that ask questions about Libre, the copper 2 ion, and the what else? Yeah, I think that's all. The one that was asking about the Libre part, the one that was asking about the copper 2 reaction, is it blessing and bless? Why are the ones that were asking these questions last time?
Yes.
Are they clear?
Yeah.
Or why should we explain? I will explain.
No, it's clear.
Fine.
It's clear.
Fine.
No,
Yes.
Yeah.
that it's fine. It should not be because Narema. No, it should be because you have understood. Is it clear? So I can ask a question. If it's clear, can I ask a question? Aye, blessing and bless. Should I ask the question? Is it clear? Is it clear?
Yes.
Yeah, it's clear.
Very clear. Okay. So what happens if here, instead of me having, instead of using glucoside, I use fructose. Then I react fructose with this copper 2 complex compound. What am I going to get? Am I going to get a positive? I just want to say, is it going to be a positive reaction and a negative reaction? Then you justify. In biochemistry, we always justify. You say, okay, it has reacted with this, and because it has reacted with this, there is not going to be a reaction because of this. There is going to be a reaction because of this. So who's going to go first? Bless or blessings?
Blessings.
Okay, so blessings, you can go ahead.
Okay, if we place like fructose in place of aldehyde, we're going to have a negative reaction because in the first place, we are supposed to have an aldehyde. Okay, we're supposed to have an aldehyde, and yeah, the aldehyde must be like libre, must be free, and the molecule must be an aldehyde. So if we use anything else in place of the aldehyde, we're not going to have a positive reaction. So we're not going to have the red precipitates at the end of the day.
Alhamdulillah. I'm even proud as a professor. I feel nice that you have learned. Now, here's a question, Blessing, here's a question. Now, what happens if the liaison, this aldehyde liaison here is not libre? What happens? We are still looking at the aldehyde. Now, what happens if the double liaison is not libre for the fructose? What if it's not libre? What are we going to have?
If it's not free, then there won't be any reaction.
Okay. So, Mr. Blessing, is it Mr. Bless? You can bless us with the answer. The same.
I know. My answer is not different from hers.
No.
Yeah, let me just
explain.
When we replace glucose with fructose, there won't be any reaction because fructose has an acetone functional group, and the carbonyl group will be occupied. Since it's not appearing on the first carbon, it will be either on the second, third, but it won't appear on the first, which means it's not free. Hence, there won't be any reaction.
Alhamdulillah, alhamdulillah. No, I'm a proud prof now. Guys, my points are at least.
Yeah.
Learn something today in the world. So we continue. The sixth reaction, which is oxidation of halogens. So we said halogens are group 17 or group 7 elements, depending on which periodic table you're using. So the oxidation is mélanger or bien douce. Mélanger means you're supposed to treat it with care. It's that type of oxidation that is very, like, you know how you handle mug cups, the way you handle mug cups, the way you handle glass cup, all those things, ceramics, etc. That's how this reaction is. It's a very delicate reaction. So we are saying it takes place in the presence, a lieu en présence. Hey, this French, this N is not supposed to be here. It's not présence. Présence there. That is iodine and bromine. Iodine and bromine in alkali milieu, in an alkali milieu. Now we are saying the same thing, It's the same thing. For us to have a positive reaction, for us to have this, for a glucose to form a gluconic acid, for a mannose to form a mannonic acid, for a galactose to form a galactonic acid, we are supposed to satisfy the same conditions, which is one, the sugar we are reacting with, is it bromine or bien iodine, is supposed to be an aldehyde. It's supposed to be an aldehyde. And rule number 2 is the aldehyde function at carbon number 1 is supposed to be libre. That's the same condition as this one. Same thing that's happening here. It's the same thing. C'est la réaction d'oxydation aussi. Ici, sixième point, c'est la réaction d'oxydation aussi. Then it means you are going to have these products. Now my question is, what happens when you react fructose in the presence of iodine and bromine? What is the reaction going to be when you react fructose in the presence of iodine and bromine? What's the reaction? What's the answer?
There won't be any reaction.
Exactly. Why? Why?
Because fructose has got
because fructose as
You see why I said you have to research on fructose and the rest, So it's because fructose is acetone and glucose and these mannose, galactose are aldehydes. So rule number 1, it's supposed to be an aldehyde. Rule number 2, the function is supposed to be free. Even if it's glucose, for as long as the carbon number 1 is not libre, we are not going to have this reaction. Take note, take note, take note. Okay, let me just give, let me show you what I mean by this here, so that we are going on the same page. I'll just show you a question in the TD, then you understand why I mean you're supposed to take note of. Says you have a haloside, dihaloside that is oxidized by bromine in an alkali solution. Then after hydrolysis and chromatography, we identify that the acid that has been produced here is gluconic. So this means, now this is how you answer questions in biochemistry. So I'm just showing you what you're going to look out for when you're answering questions. So if there's oxidation, it's either going to be positive or negative. Now here they are saying that we have a gluconic acid. It means it's a positive reaction. It has satisfied the 2 conditions. That is, 1, it's an aldose, which is true. Which is the second one, it's carbon number 1 is libre. It satisfies this condition. The bromine has finally oxidized a glucose molecule called either A or B, and we have the formation of gluconic acid. Is it clear? Is it clear on this part? Is it clear?
Yes,
it clear? Is it clear?
Clear.
Then another question. I'm not going to answer these questions now. We'll answer them later on. But I just want you guys to understand.
It's clear.
So exercise 3 states that we have a triholoside DM. Then after chromatography, we obtained 3 distinct tasks. Then we're saying that we reacted this with liquid defemine. Now, liquid defemine is what this copper reaction we are talking about. The copper reaction that gives the brick rouge precipitate. Now, they're saying il donne une réaction négative. So if it's a reaction that is negative, it's either it did not satisfy the two conditions, or there's one that is not being obeyed. When the first one, we can say, okay, maybe in this function, in this whole glucid, triholoside, we have, instead of us having an aldehyde, maybe we have a cetone. That can be hypothesis number 1. Hypothesis number 2 might be, say, okay, it can be an aldehyde, but the carbon number 1 is not libre. It is for this reason why we have a negative reaction. So we have 2 conditions. So okay, now say, okay, the first one might be the carbon number 1 is not libre. This is why we have a negative reaction. The second one might be, okay, maybe it's a cetose. Okay, if it's a cetose, this reaction will be positive because it's supposed to be carbon number 1 and not carbon number 2. Is it clear for Femin? Like, this is application how you guys go ahead in the TD. Is it clear? Is it clear?
Yeah, it's clear.
Yes,
It's clear.
Then if it comes to the reaction, the iode foot. So we're saying il n'oxyde pas, supposed to be S here. Il n'oxyde pas par l'iode on milieu alkaline. So it means there is no reaction in the alkaline solution. It also means that it did not satisfy the conditions, which are 1. The carbon number 1 is supposed to be libre. Number 2 is supposed to be an aldehyde. So in a case where it's an aldehyde and the carbonyl function is not libre, then the reaction is not going to happen. There will be no reaction. If it's an aldehyde and the carbonyl function is not libre, we're not going to have a reaction. But if it's a carbonyl and it's a cetose, still the reaction is not going to happen because it's a cetose. It's a cetose because the conditions that we have state that we are supposed to have a reaction at the carbon number 1, and that function for that reaction should be an aldehyde. Should be an aldehyde. So this is how you apply these reactions in your travaux dirigés. Is it clear? Is it clear?
Yes, it is.
I think I'm kind of boring, man. I'm guys. Anyway, we continue.
I'm done. It's not important. I'll see at the end.
You can see.
I have a question. On the same halogens, is it only iodine and bromine that react with the sugars to produce a positive result, or maybe all the halogens, even chlorine and the other?
No. For my study, we only looked at these 2 halogens, but I'm pretty sure these other ones would also react, because you see the halogens are special metals, special non-metals, in the sense that their negativity increases as you go. The electronegativity increases as you go on top. Then the ability to become solvents in substances decreases as you go on top as well. So you find acids like hydrofluoric acid is a very, very weak acid, even though it has chlorine. Fluorine is considered to be the most reactive element on the periodic table. But even if it is the most reactive element of the periodic table, when it is engaged in a liaison with hydrogen, it does not form the strongest acid, but forms a weak acid. So in the same way, it does not mean that when we do not have fluorine, chlorine, astatine, they are not reacting with the glucose, the glucides. It might be their reaction. We say this is a reaction douce. We said it's a soft reaction, it's a cool reaction, it's a slow reaction. If bromine and acetylene, bromine and iodine were to react in a very slow way. Now, these two are not very active elements on the halogens table. They're not very reactive elements on the halogens table. It might be very, 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 very slow for fluorine and chlorine. Maybe it may be very, very fast for acetylene that you cannot even observe the reaction. So maybe it was found that iodine and bromine are the best to react glucose or glucid molecules to determine which one forms an acid over the glucose molecule. So in other words, what I'm trying to say is, personally, I've not done a research on which one reacts, if it's fluorine that is going to react with the glucose, the glucides to form the acid over that sugar. But I am saying there might be conditions like maybe fluorine reacts very, very, very slow as compared to iodine and bromine that we have in this case. So what I'm trying to say is, please, bosses, do a research on that one, because in my study, we've only looked at iodine and bromine. And when you're done with the research, please, like I said, when you're done with the research, you also tell me that, okay, I found this, because I'm also learning. When I'm teaching you guys, I'm not only teaching myself. I'm not only teaching you, I'm also teaching myself, because there's certain things that I also do not know. I'm also just like you guys. I'm also a student. I'm also learning these things. Yeah. So when I ask you guys to research for something and you find out something, you say, oh, bosses, I found out this, then I also add on to my knowledge. When the people come next time, I'll say, no, Mr. Blessing did this, because I remember Mr. Blessing for the rectification he gave me in organic chemistry. I'll forever remember Mr. Blessing, even in my exams when I have a question on nomenclature. So that's the idea. You build information from the information that you find from other people. Yeah. So, Mr. Blessing, please, it's a research. When you're done, please share with me. I'll be very happy. Then, are there any questions on oxidation by the halogen? So, whenever a halogen is reacted, that is bromine and iodine, in an alkaline solution with the two conditions, that is, one, it should be an aldehyde. Two, it should have a carbonyl function that is libre. We are going to have the formation of glucose acid. Glucid acids. That is, in the case of glucose, we are going to have acid gluconic. In the case of mannose, we are going to have l'acid manoic. In the case of galactose, we are going to form the acid galactonic. Now, here is a question on call. Now, what if we react bromine to fructose? What are we going to get if we react fructose with bromine or iodine? What are we going to get? Is it a reaction that is going to be positive, or is it a reaction that is negative? And please justify your reasoning. Are we there?
Yes, we're clear.
What answers, guy?
So, like, we have a negative reaction in that fructose contains the carbonyl group on the second carbon. Yeah. So meaning it's a cetone, and like the requirement of a reaction, it has to be an aldehyde, meaning the carbonyl group has to be the first carbon.
Okay, thank you very much, Mr. Konwani, for that response. So basically, the idea is we are supposed to satisfy the two conditions, which is the first one, we are supposed to have an aldehyde. The second one, the aldehyde is supposed to be defined on carbon number 1. Anything not defined at carbon number 1 will not react, because that would mean that is a cetone and not an aldehyde. And furthermore, the aldehyde is supposed to be libre. It's supposed to be libre and not to be engaged in any liaison, either bit glycosidic liaison or bien it being oxidic liaison. Anything, any questions before we forge ahead? Okay. Ozazone. So we said an ozazone is formed when you react glucose. So these are the examples. When you react glucose, fructose, and mannose with phenylhydrazine. So, I don't know if it's Mr. Nan who asked this question. Why is it that you do not have galactose as an ozone? So my response was, it's basically because, you see, in these molecules, the difference that lies between these molecules is basically the functions, the hydroxyl functions, where they are, either on the left or either on the right. This is why we have epimers, there are stereoisomers, enantiomers, etc. So the reason why galactose is not found amongst these, take note, these ozones that you can see here, these ozones here, they are the same. They are the same. The reason why we do not consider galactose in this case to be one of the ozones is because maybe its structure, we'll talk about two factors here. We'll talk about its structure being different from the three, or we also talk about its chelarity. So we talk about the chelarity of galactose to be different from the chelarity of these molecules here. It is found that after the reaction of phenylhydrazine, where the formation, if you look at this, the hydroxy is here, it's like they're the same, they're like the same. But uku, you have carbonyl, uku, hydroxyl. Here, you have carbonyl kumamba uku pa. This is a acetose, because this is fructose. Then this is what is it? It's aldose. So if you look at the structure of this and this, they're all different. Even when you look at the carbons that are symmetric, you find that they are different. They are different positions. So we can state that the contributing factor to why galactose does not occur as an ozone might be because of its chelarity, or maybe because of its carbon asymmetric. There are carbon that are symmetric at different positions as compared to these three. We might say, okay, this one is at position 1 and 2, this one is at 1 and 2, 1 and 2. Maybe that of galactose is at position 3 and 4. So because there is a difference in which carbon atom is asymmetric, even the type of ozone that is going to be formed will be different from that of fructose, mannose, and galactose. So in this case, we have fructose, which is different from glucose, which is also different from mannose, and mannose is also different from glucose. But when they are all reacted with phenylhydrazine, will give ozones, and these ozones are identical. So the ozone for glucose, the ozone for fructose, and the ozone for mannose are identical. So we are going to call the one formed by glucose as glucosazone, also known as D-glucose phenylhydrazone. For fructose, we're going to call it fructosazone, which is going to be called D-fructose. So please take note, the D stands for the dextrogyl orientation of optic rotatoire. So we're going to call it, what is fructosazone, also known as D-fructophenylhydrazone. And the last one, mannose, will be called mannosazone, also known as D-mannose phenylhydrazone. Are there any questions? So before I allow a question, I'll give a recap. So we said ozones are formed when we have a glucose molecule or a glucide reacting with phenylhydrazine. So phenylhydrazine necessitates a reaction and the formation of ozones. So is it Mr. Blessing that again asked the question to say, boss, why is it that you do not have a galactose ozone? So the response is basically the idea or the reason why we do not have a galactose ozone appearing amongst these ones would be because of chelarity. Now, chelarity comes in as a condition of the carbons that are asymmetric. So we gave an example. Take, for instance, the carbons that are asymmetric. In this case, we have 1 and 2. We have another one, 1 and 2. We have another one at position 1 and 2. Oh, we have almost the same positions, 1 and 2, 1 and 2, 1 and 2, 1 and 2. Now, take for instance, galactose has position 2 and 3. Because there's that type of change, even the type of ozazone that you're going to produce, that of galactose, will be different from these three that you are seeing here. All in all, when glucose, mannose, and fructose react with phenylhydrazine, they form what you call identical ozazones. When you look up this either on Google, etc., they form identical ozazones. They form identical ozazones. Additionally, we would say, okay, galactose, because they explain the principle of chelarity and the importance of chelarity, would be because examples like aspirin I gave, say maybe the orientation is in the opposite direction. For example, it's a D orientation of galactose, and we are dealing with L-oriented glucose, mannose, and fructose. Because of that case, we cannot have a type of ozazone that is going to be identical to these four or to these three basic sugars: fructose, mannose, and glucose. Are there any questions before we go any further? So we are on reaction with. Réaction 8. La perméthylisation. Reaction de la perméthylisation. So we say the reaction de la perméthylisation is a way, or bien it's a type of analysis that we use to determine which bond we are actually studying. So, like I said earlier on, we have how many types of liaisons? We are in the biochemistry of Glucides. We have two. We have the first one, which is called the Glycosidic Liaison, and the second one, which is called the Oxidic Liaison. So the oxidic liaison is basically made from the orientation of the first carbon atom of a glucose molecule with the fifth carbon atom of the same glucose molecule and forming what we are calling a purine. Then we have compounds or molecules like fructose forming a bond with the first carbon atom and the fourth carbon atom. They form a structure that looks like a pentagon, and the type of liaison is called a purine. So basically, perméthylisation is a reaction or a way we can use to determine which liaison we are discussing on or talking about. So we have reactions like here where we have the iode, the methyl reacting with the libre hydroxyl ion, or not ion, function to form an ether. So we said an ether is an oxide of an organic compound. It's an oxide of an organic compound. So if it's an oxide of an organic compound, then it's supposed to be different because all organics, we know that all organic, all oxides are formed from maybe a metal plus oxygen, a carbon plus an oxygen, non-metal plus oxygen, they form oxide. Now, when we're talking about organic compounds and we're saying it's an oxide, so we want to differentiate the oxide formed from normal organic compounds to the oxide of this one, which forms the ether. So we said an ether is formed from ara, which is the rest of this molecule, and an alkyl group. An alkyl group is any alkane with one hydrogen atom less. Now, in this case, because we are using a reactant by the name of methyl diode, which is iodine and the methyl function, we are going to have an ether formed with an alkyl called methyl. Methyl will be our alkyl. So in this reaction, what we are supposed to now take into consideration is the free hydroxide liaison. So for the reaction to take place, we are supposed to have a free hydroxyl liaison. Let it be, it can either be, now in this case it's different, it can either be an aldose, it can also be a cetose. So here we don't have exceptions. Why? Because this whole reaction basically just shows us which liaison or bien which pont we are talking about. Either the purine, which is formed from the aldose, an example is glucose, or bien the furine, which is formed from the cetose, an example is fructose. Then we can also have it determining which liaison is glycosidic in a chain. Are there any questions? Okay, before the head. So the last reaction, which is la réaction ou bien l'action de l'acide périodique, which is HIO4. So we said acid periodic just cuts these glucides into two principal parts. These two principal parts here, we have got what you call the part here on top, right? The part here, Kumoroko, is called the, where is it? Ukumoroko, it's called the, is it the function? Is it the what? Is it the primaire? What forms formic acid? Formic acid is here. Aldehyde formic acid. Formic acid is here. Yeah. And this is a aldehyde formic. So we are saying formic acid will always be formed from the primary alcohol. The primary alcohol. So in organic chemistry, when we talk about nomenclature, we will learn that they are what you call primary, secondary, and tertiary substituents. So we are going to look at that later on in nomenclature, how we name compounds when you have a primary, tertiary, and a secondary substituent. Now, in this case, we have a primary, I'll call this substituent, or I can call it, because you see here, okay, so we can call this a substituent with a hydroxyl function, and it is a primary alcohol. It's a primary alcohol. So, which is this one here, acid formic, which is this one here. It's acid formic. So with the CH2, or how come we won't have it? Or no, this aldehyde function would define the acid. Yeah, formic. So this whole thing here, because this is acid formic is a carboxylic acid. Acid formic is a carboxylic acid. So this carbon atom and the function here, the what do you call it? The what is? I'm going to explain. Acid aldehyde formic is this one. Aldehyde formic is this one. So CH2, okay, balances this one. Then acid formic, which will be this one here. So we have one carbon atom and hydroxide with a hydrogen forming a carboxylic acid. Now this one forms, we said at the carbon number 1, we are supposed to have a liaison with the oxygen to form an aldehyde. So this thing can be called an aldehyde. Where is it, Joe? Just a minute. This thing gives the aldehyde. So this whole thing here gives the aldehyde function. Then plus one hydrogen atom. This is a basic aldehyde. It will be called methanol or bien aldehyde formic. Aldehyde formic. So basically, the acid periodic is used. The acid periodic is just used for. Can you guys see my pointer?
Yes.
Yes.
Hey.
Yes.
You can't see it. Can you see it?
Yes, we can.
Guys, anyway, let's finish. So we are saying this function here is the aldehyde function and forms the acid formic, and our acid formic in this case would be our acid formic in this case will be formed from the primary alcohol. Then the last one, which is aldehyde formic, and this is acid formic. It will be formed from our alcohol second. So what acid periodic does is just cut the glucose or bien the glucide molecules in these distinct points. So you're going to have a part that contains maybe the primary alcohol, maybe the other side would be the secondary alcohol. It is not conventional that we are going to have this type of orientation. Like I always say, this is just for simple understanding. You can also have this type of orientation where you have the secondary alcohol on top, like that, and the primary alcohol below. So what acid periodic does is just cut these molecules in two distinct parts. It cuts one in one portion where you are going to have the formation. It cuts one in it's going to cut one in a way that you are going to have this alcohol, primary alcohol, being divided to form an aldehyde formic, or it's going to also cut this molecule so that when the glucose, when the cutting is done, this secondary alcohol can give this acid formic. So it's always that when you have reaction the periodic, you are going to have these two products that are going to be formed. So from your acid, from your alcohol premier, you're going to have the aldehyde formic, and from your alcohol secondaire, you're going to have your acid formic. Are there any questions?
Quick question, boss.
Yes, sir.
The acid formic and the aldehyde formic, is it one compound?
No, they're different. This one here is okay. Look, they are all coming from the same function. They're all coming from the same function. Why do I say, oh no, they're not the same function? So we have this one here. It's an aldehyde. Now, an aldehyde that only has one hydrogen atom is called methanol. Let me just write it. This is now where the norm usual and norm thing come in. Right? So meth. So the UPAC name for aldehyde formic is methanol. So aldehydes end in this type of terminaison. The suffix for aldehyde, so when you look at nomenclature for aldehydes, we have this type of terminaison. Then for alcohol, we have LO. For cetones, we have ONE. So la norme usuelle, the one that we use normally to just define this compound here, is aldehyde. Why? Because you have an aldehyde. Now the simplest aldehyde we have with one hydrogen atom is methanol. Now formic is also the AKA. So you can call it methanol or bien aldehyde formic. Same applies to this one. The simplest carboxylic acid we have is methanoic acid. Kapera guys na numbers one. Methanoic acid. The simplest acid we have from the carboxylic acid is methanoic acid. Methanoic. You guys know how to spell methanoic, eh?
Yes.
Onirembe. Methanoic acid. Let me write. Pale my restaurant on this. Methanoic. Methanoic. Methanoic acid. So this is methanoic acid, and this is methano with LAL terminaison. So basically, acid periodic just cuts these glucose sugars or the glucose. You see what they are showing here? You're just cutting. So l'acide périodique coupe la liaison convenante entre atomes de carbone adjacents voisins porteurs de hydroxyl libre. It's always the ones that are free that are going to be cut. If you are engaged in a liaison, it is the same principle wherever you go, even in relationships. You are never supposed to engage yourself in any other type of liaison if you are already in a liaison. That now becomes what you guys call an entanglement. So, are there any questions? Any questions? Because next, it will be travaux dirigés avec Monsieur Laston. Are there any questions? Are there any questions? I'll start asking questions number. So, Tiamba. Code one. Moses, what's an aldehyde? I'll be giving, before we even close, I'll ask questions 1, so that I know that you've understood. What's an aldehyde?
Oh, yeah. So an aldehyde is an organic compound that contains a carbonyl group in its first level of the carbon.
Mr. Blessings, what's the difference between perméthylisation and réaction d'oxydation avec méthotransition? What's the difference? Or just describe what perméthylisation is and what the réaction d'oxydation avec the metal de transition, what it is also. Please describe the two reactions. Don't give a difference. Just describe the two. Up any point up. Okay, no questions. Random.
The perméthylisation is simply an analysis that we use in order to determine whether what we are dealing with is an aldehyde or a ketone. Yeah, then oxidation. Okay, the other one has to do with the reaction of sugars with transition elements, and we are told that there are supposed to be two conditions that will make the reaction to give a positive response. And the first condition is that the sugar has to contain an aldehyde functional group, and the second one is that it has to have a carbonyl group which is libre for it to give a positive result. I think that's it.
So in a case where we have fructose in the place of an aldose, or bien acetose in the place of an aldose, what happens to the reaction?
There is no reaction.
Okay. So Liliane Musonda, what's the difference between la perméthylisation and la réaction avec l'action de l'acide périodique? What is the difference between la réaction de perméthylisation and the réaction ou bien la action de l'acide périodique? You can describe them as well if you want.
Okay, let me try. Perméthylisation is, just like Luciano said, a reaction it's simply a reaction that's used to determine which bond is being talked about. And then it's supposed to have, in order for us to carry out that same perméthylisation, you have to have a free hydroxyl liaison. And it can, for perméthylisation, it can either be an aldose or a ketose. It's not just restricted to being an aldose. Then for the periodic acids action, this one, it simply cuts. It cuts the, don't know if I would say compound or something, but it cuts it to give an acid. Yes, that is so that.
You've not finished. It gives what? I said 2 acids. It gives 2 acids.
Yeah, it gives methanoic acid and aldehyde formers. I've forgotten that. Yeah.
So please revise, right? Revise. So we are going to go to Mr. Kennedy. What's the difference between the ozazone, glucosazone, and fructosazone? What's the difference? Between
fructosazone and which one?
Fructosazone and glucosazone. What's the difference there? What's the difference?
Oh la la.
What is the difference, Mr. Kennedy? What is the difference, sir? What's the difference?
Yeah.
Never pena. Never.
Yeah.
Okay, there is no difference, Mr. Kennedy. The glucosazone for glucose, fructose, and mannose are all the same. There is no difference, right? There is no difference.
Yeah, they are all the same.
Yeah, they are all the same. But no, there's another question I'm going to ask. There's another question I'm going to ask. No, as in I've answered this question. So the question goes like this.
Okay.
For example, we have a, how can I ask this question? Okay, I'll use the code to ask this question. What's the difference? What's the difference between a furan type of liaison and the purine type of liaison? What's the difference?
Did you just say purine twice?
What's the difference between the purine type of oxidic bond and the furan type of oxidic bond? Yep, guys. Yep. I think I should be doing this for organic chemistry. So,
sorry, but remember purine, the same thing.
No, I'm saying
am I hearing the same
purine and the furan.
Purine and furan.
No, it's purine and the furan.
Yeah. Okay, so for the purine oxide bond, of which it makes some pentagon kind of shape, it is formed from an aldose function. While for the furan, it is formed from the ketose function group, of which the bond is between the first and fourth carbon. Yeah, I just forgot to mention that on the purine, it was on the first and fifth.
So give me an example of one that forms the purine and the other one that gives a furan. Examples of glucides that form the purine and the one that forms the furan.
Okay, so for a purine, we can use glucose.
Furan,
seeing that it is formed from a ketose, we're going to use that as fructose.
Exactly. So you see the reason why I asked you guys to actually research on which one is the difference between fructose and the rest. It's because of this, because you always use the same principle. Always know that fructose is the only ketose and the rest are aldehydes. So we got to who? Atifumbani Sichali. Boss, what is the what does it mean for a glucose molecule to have the ability to not. What do you understand by this property, pouvoir rotatoire ou bien pouvoir optique rotatoire? What do you understand by this property?
It's 7 o'clock.
Pouvoir optique rotatoire. Mr. Kondo, you've already answered the question, eh?
Oh, yes, boss. But
yeah. You have a question? Mr. Who is this? Mr. Fumbani.
What's the question again?
The question is what do you understand by the term pouvoir rotatoire ou bien pouvoir optique rotatoire?
Okay. What I understand from that is that, for example, it's all about the structures that we have for the D fructose and the how do I explain this? Okay, it's got something to do. It's got something to do with the L, where the hydroxide switches sides, where we have the L and then we have the D kind of arrangement.
So what causes the D and L type of arrangement? What causes it?
Okay, what causes the D kind of arrangement is a situation where we have the asymmetric carbon having the hydroxyl group on the right side, the right hand side.
Okay.
Yes.
Okay. Basically, the reason why you have D and S is just the ability or bien the affinity of the molecules towards light or away from light. So, like I said, for those that want to go in detail about how molecules interact with Lumiere, you can look up spectroscopy. Then it's 19 hours and we are going to finish. Don't worry, Mr. Kondwani, we are going to finish. So we go to Esther. I have a question, Esther. Now, we mentioned to say that for us to satisfy the reaction of permeabilization, we are supposed to have a carbon atom number 1 for the aldehyde. It's supposed to be libre. Is that true? As in, for reaction de permeabilization, we said the carbon atom number 1 is supposed to be libre, isn't it? True or false? True or false? True or false? Is it supposed to be libre? Or maybe if it is true, please justify. And if it's false, please justify. So the question is, d'après la réaction de perméabilisation, we say that the carbon number 1 for the aldehyde is supposed to be libre. Is it true or it is false?
It's true.
What's the justification?
Because if it's not libre, then it's already okay. You give an example of how catalysts and enzymes, if the enzyme is already bonded to a substrate, it won't react. So if it's not free, then the reaction won't take place, and we won't find the position of the bond of the
liaison. Okay, so the answer is actually false, because the reaction de perméabilisation only takes place when you have free hydroxyl functions. Free hydroxyl functions. That is the reaction de perméabilisation. Yeah. So we go to blessings. Have you already answered the question?
Yes, in spirit. No, not yet.
For saying in the spirit, what reaction is responsible for the formation of ozazone, fructoozazone? For saying in the spirit, they've got 2 questions. So this is the first one. So So the first one is like this: what is reacted with fructose to give fructoazazole? What is reacted with fructose to give fructoazazole?
Fructose and phenylhydrazine.
Ah, okay, phenylhydrazine. Okay, you're in the spirit zone. Then the other one is what's the difference between D-mannose and L-mannose?
D-mannose.
What's the difference between D-mannose and L-mannose?
I think they are chirality.
They are?
Or the position of the chiral center.
Ashan, what do you say? I can't get you. Network is cutting.
The difference is the position of the chiral center, like the bond where you have oxygen and hydrogen is different. Though the structure is the same, the molecular formula is the same.
Okay, so basically the difference between mannose, D-mannose, and L-mannose, there are two. You can either answer it in this way. You can say they are enantiomers of each other. That's number one. Or bien, you can say one has the dextrogyl orientation, the other one has the levogyl orientation. Now, I think everyone has answered except Taonga, eh? So, Taonga, the question is, I even forgot. Let me even go in the coup. Maybe we can even find the question in the coup. So, my question is, what happens when you react, what's this? What happens when you react glucofuranosyl 1,4 fructofuranosyl with sulfuric acid? What happens when you react glucofuranosyl 1,4 fructofuranose with sulfuric acid? In other words, what happens when you react a sugar with a strong acid? What is given as the end product?
I'm not sure, but I think a salt is given.
Salt?
No, wait.
So when you react an acid 4 with a carboxyl, when you react with glycofurasyl 1,4 fructofuranose, you will get a fural. So a fural is what you get when you react a glucose molecule or bien a glucide with an acid 4. So that ends our coup for today. It was a great time with you guys. On se verra, Inch'Allah, la semaine prochaine pour la chimie organique et la chimie générale. So for you guys that are doing chimie générale, I think you'll be attending class with Atomistic on Sunday. I was told, hey, this class scheduled for Sunday.